What if you fell into a black hole? Not in theory, but you right now. Imagine drifting through space when suddenly, the pull becomes too strong. You've crossed the point of no return, the event horizon. There's no going back. Light can't escape, time slows down, and your body begins to stretch, first your toes, then your legs, then your chest, as gravity tugs harder on your feet than your head. You're spaghettifying, turning into a long strand of atoms, stretched by a force no human has ever experienced. But here's the twist: what if you don't die? What if instead of being crushed, you pass through a wormhole? What if the black hole isn't a dead end, but a tunnel to another universe, another dimension, another you? In this video, we'll explore every terrifying, mind-bending, and scientifically daring possibility of what might happen if you went into a black hole, and somehow lived to tell the tale. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The idea sounds absurd. Everything we know about black holes screams one truth: fall in, and you're gone forever. No calls for help. No final words. Just oblivion. But in a universe governed by both unbreakable physical laws and tantalizing theoretical loopholes, maybe, just maybe, there's a sliver of a chance. A hidden route. A loophole in reality. Let's begin at the event horizon, the point of no return. From the outside, a black hole is defined by three things: mass, spin, and charge. Strip away everything else: stars, matter, energy, and what remains is a singularity wrapped in an invisible cloak. That cloak is the event horizon. Cross it, and even light can't escape. But let's imagine we're aboard a futuristic spacecraft, sleek, shielded, and riding the edge of science fiction and cutting-edge theoretical physics. Our destination, the singularity at the heart of a rotating black hole. Not just any black hole, but a Kerr black hole, one that spins with unimaginable velocity. Why a Kerr black hole? Because it's the only kind, according to some physicists, that might offer a safe passage through. Approaching it is anything but safe. As you get closer, you notice space itself isn't still. It begins to swirl around the black hole like water circling a drain. This effect, known as frame dragging, means the fabric of space-time is being twisted by the black hole's rotation. You're no longer orbiting the black hole in the traditional sense. You're being dragged around it. Now, consider tidal forces. In a stellar mass black hole, the difference in gravity between your feet and your head would stretch you apart violently long before you ever reach the event horizon. This is spaghettification, an elegant term for an ugly death. The gravitational gradient is so steep that atoms themselves are pulled apart. You're turned into a long, thin filament, thinner than a human hair, longer than a skyscraper. And then you're gone. But not all black holes are the same. Supermassive black holes, millions or billions of times the mass of our Sun, have much gentler tidal forces at the event horizon. You might cross it without even realizing it. No alarms. No disintegration. Just an eerie silence and a growing sense of inevitability. Let's say we pick such a black hole, Sagittarius A*, the one at the center of our galaxy. Its event horizon is vast, larger than the orbit of Mercury. As we approach it in our theoretical spacecraft, shielded with exotic matter to repel radiation and gravitational stress, we find that the ride becomes strangely smooth. Time dilates. Outside observers would see us freeze in time at the edge. To them, we never fall in. But inside, for us, time continues. Now here comes the real terror and intrigue. Inside the event horizon, space and time switch roles. You are no longer moving through space toward the singularity. You are moving through time toward it. Escaping is no longer a matter of thrust or speed. The singularity is in your future as surely as tomorrow. No force in the universe can alter your course. But what is the singularity? According to Einstein's general relativity, it is a point of infinite density, zero volume, where the known laws of physics collapse. Time ends. Space ceases to be. It's not a place, it's a boundary beyond understanding. But quantum physics, ever the rebel, refuses to accept such absolutes. It whispers possibilities: quantum foam, Planck scale geometry, string vibrations, loop quantum gravity, each offering a glimpse at what might lie beyond the singularity. Suppose, then, that the singularity isn't a dead end but a bridge. Enter the Einstein-Rosen bridge, a wormhole. Some solutions to general relativity suggest that rotating black holes might connect to white holes, cosmic fountains that expel matter. Fall into one end, emerge from the other. A cosmic subway between regions of space-time. But these bridges are unstable. They collapse before you can use them. That is, unless we find a way to prop them open, perhaps with exotic matter, hypothetical material with negative energy density. Could we harness such material? We don't know. But theories like the Casimir effect in quantum field theory hint that negative energy might exist under very specific conditions. Perhaps a future civilization could generate and stabilize this material, building a wormhole highway across the cosmos, or a single tunnel through one black hole. Now picture it, our spacecraft, laced with exotic shields, guided by AI navigation systems that predict and counter gravitational fluctuations in real time, diving into a supermassive rotating black hole. Past the event horizon, past the accretion disk glowing like a demon's eye, deeper into the darkness. Tidal forces are bearable. Time has slowed to a crawl. The singularity looms, but it's not a point. It's a ring. Yes, in a curved black hole, the singularity is a ring of rotating matter. Some solutions suggest that it could allow passage into a different region of space-time. Theoretically, you could avoid the singularity altogether if you passed through the ring's center. It wouldn't be easy. It would be like trying to thread a needle while falling through a tornado. But if done perfectly, the laws of physics might just bend in your favor. And if you pass through, you might emerge into a new universe. Or a different part of ours. Or you might not emerge at all. Perhaps consciousness would be transformed. Perhaps time itself would lose meaning. There are other theories too. In string theory, black holes may not have singularities at all. Matter collapsing into a black hole might be replaced by a fuzzy ball of strings, black hole fuzzballs, eliminating the need for infinite density. In this scenario, survival might be possible, though the environment would be unimaginably chaotic. Another possibility, the firewall paradox. In some quantum models, the event horizon becomes a zone of intense energy, a firewall that incinerates anything falling in. If this is true, then the moment you pass the event horizon, you're destroyed by quantum effects. There is no journey inward. Only annihilation. But the paradox remains unresolved. Hawking radiation, information conservation, holographic principles, all challenge the notion of a traditional black hole. Some physicists suggest black holes don't destroy information. That what falls in is encoded on the event horizon itself, a 2D record of a 3D reality. In that case, maybe we don't fall in at all. Maybe we become part of the surface. Still, for the sake of thought experiment, we push onward. The forces increase. Even in a supermassive black hole, as you approach the singularity, you cannot avoid the end forever. At some point, even the strongest materials known to science would shatter. Atoms would stretch. Quantum forces might try to hold you together, but the gravitational gradient would win. And yet, just before the end, strange things might happen. You might witness the entire future of the universe in fast forward. Stars dying, galaxies fading, entropy taking over. Time might compress into a final moment, giving you a cosmic epiphany, a flash of ultimate understanding. Or perhaps your consciousness, ripped from your body, becomes part of the singularity itself. If the black hole leads to another universe, perhaps you are reborn in a different cosmic inflation, where the laws of physics begin anew. We don't know. That's the truth. Every theory, every speculation, is a step into the unknown. But what we do know is that black holes are no longer just the monsters of space. They are laboratories of reality, testing grounds for our boldest ideas. If humanity is to survive its curiosity, we must look into the abyss, not just with fear, but with wonder. And maybe, just maybe, the abyss will look back with a smile. As we continue our descent into this cosmic abyss, let us pull ourselves deeper, not just into the black hole itself, but into the countless theoretical implications, paradoxes, and questions that orbit this mysterious gravitational leviathan. Each new layer we peel back reveals another cascade of implications, each more mind-bending than the last. Imagine that we have now passed the innermost stable circular orbit, the last place where a satellite can orbit a black hole without spiraling inward. Past this point, there is no turning back. Our fictional spacecraft is equipped with the most powerful computational models ever devised, using advanced simulations built on decades of quantum gravity theories, general relativity, loop quantum geometry, string theory harmonics, and machine learning designed to adapt to the unknown in real time. Even still, we are venturing into terrain utterly alien to anything we've ever explored, territory where not even mathematics behaves the way we expect it to. Outside, the world is being torn apart by extremes. Space-time is twisted, stretched, curved, folded into surreal geometries. Concepts such as up, down, left, or right no longer hold coherent meaning. Space is no longer something you move through, it moves through you. Time no longer behaves as a single arrow. It feels almost as if it loops, slows, and rushes forward unpredictably. What does a second mean here? What is a year? In the gravitational embrace of a black hole, time becomes deeply personal. An observer outside the event horizon might watch billions of years go by in what feels like mere minutes to us. Entire civilizations may rise and fall while our journey continues inward. Let us return to spaghettification, one of the most dramatic and well-known phenomena associated with black hole physics. While it's often portrayed as instant and violent, the exact experience of spaghettification depends heavily on the mass of the black hole. In a stellar mass black hole, the distance between the gravitational pull on your feet and your head becomes so extreme that your body is stretched into a long, thin strand. Every bone, muscle, atom, and subatomic particle is aligned like a spaghetti noodle in a gravitational gradient so intense that even molecular bonds are meaningless. You're not just pulled apart, you're unraveled. But in a supermassive black hole, say one with a mass 10 billion times that of our Sun, the tidal forces at the event horizon are much more forgiving. You may pass the boundary without even realizing it. Spaghettification is delayed. The interior feels deceptively calm. It's not until you get closer to the center, past the ring singularity of a rotating curved black hole, that the real distortions begin. Now let's shift our focus to the concept of naked singularities. A naked singularity is a hypothetical singularity without an event horizon, a gravitational singularity exposed to the rest of the universe. In such a scenario, we would be able to observe the most extreme region of space-time, potentially gaining insight into the laws of physics at their breaking point. This would violate the cosmic censorship conjecture, a principle introduced to prevent such possibilities. According to the conjecture, nature hides singularities behind event horizons, keeping the madness out of sight. But what if cosmic censorship is wrong? If a naked singularity could exist, and if we were to travel into it, then perhaps we'd witness space and time behaving in ways we've never considered. Perhaps we'd see the very foundation of causality break down. Events might occur out of sequence. The effect might precede the cause. Past, present, and future might lose their order. Memory and prediction might become interchangeable. Could consciousness even survive such disorder? Let's go further still. There are quantum interpretations of black holes that suggest the singularity is not a point at all, but a dense structure of tangled quantum information. Loop quantum gravity, a theory attempting to unify quantum mechanics with general relativity, proposes that space-time itself is quantized. Instead of a smooth continuum, it's made up of discrete chunks, or loops, and under extreme gravitational compression, these loops create a quantum bridge known as a Planck star. If this is true, then the collapse to a singularity halts before infinity is reached. The black hole instead becomes a portal to something else, perhaps another phase of the universe. Some theorists propose that black holes could be the seeds of new universes. The matter consumed by a black hole might not be destroyed but reborn, expanded elsewhere into a fresh cosmic bubble. In this view, every black hole could be a Big Bang in its own right, spawning a new universe with slightly altered physical constants. Perhaps we live inside one such offspring right now. Perhaps the very beginning of our universe, the Big Bang, was the result of matter collapsing into a black hole in a parent universe. What does that imply for our journey? If we could survive long enough to reach the Planck core, or whatever structure exists instead of a singularity, we might find ourselves at the boundary between our universe and another. We might emerge into a fresh cosmos, unformed, rapidly expanding, alien in every conceivable way. Perhaps gravity behaves differently there. Perhaps time has never begun. Perhaps life, consciousness, and even the laws of motion are entirely rewritten. Now let's explore more speculative means of surviving such a journey. We must consider the idea of manipulating spacetime directly. Alcubierre drives, which use a bubble of warped spacetime to move faster than light without violating relativity, might be repurposed for navigating black holes. If we could generate such a bubble, perhaps we could insulate ourselves from the gravitational effects inside the event horizon. We wouldn't travel through space, we'd take space with us. Such a craft would require exotic matter with negative energy density, something we have never synthesized in large quantities, but have seen glimpses of in quantum effects such as the Casimir effect. Theoretically, a region of negative energy could counteract the crushing effects of gravity, protecting the ship and its passengers from spaghettification. What about using quantum entanglement to preserve consciousness? If your mind could be entangled with an identical quantum system outside the black hole, then theoretically, the information could remain accessible even after the body is destroyed. This ties into the black hole information paradox, whether information is truly lost in a black hole or merely scrambled. Stephen Hawking suggested that information is not destroyed but encoded on the event horizon and eventually released through Hawking radiation. So could your consciousness be restored? Could you upload yourself before entering and be downloaded from the Hawking radiation that escapes billions of years later? Or could we use black holes as computers themselves? The concept of a black hole as a hyper-efficient quantum computer has been explored in physics. The surface area of the event horizon, not the volume of the black hole, determines how much information it can store. This gives rise to the holographic principle, the idea that the universe is fundamentally two-dimensional and what we perceive as 3D is a projection. A sufficiently advanced species might use black holes as consciousness servers, transferring themselves into the horizon itself to survive indefinitely as pure data. And what of simulated realities? If black holes are portals to other dimensions or universes, could they be access points to a multiverse simulation? A kind of cosmic reboot button? If we're inside a simulated universe, perhaps passing through a black hole allows us to escape or upgrade to a higher level simulation. Perhaps the singularity is a universal exit code. Could we travel through time? Black holes bend not just space, but time. The intense gravitational field dilates time so much that a few minutes inside could equal millennia outside. If you could escape a black hole's grip, which seems impossible under current physics, you might return to a universe unimaginably far into the future. Stars gone. Planets dead. Only blackness and entropy. Would that be survival? And if so, would it even be worth it? Even this doesn't touch the deepest questions black holes raise. What happens to identity, consciousness, and self when subjected to gravitational extremes? If your atoms are pulled apart, if your time slows, your perception alters, your physical self is destroyed but your informational pattern remains, are you still you? Are you the sum of your molecules, or the pattern they form? Could a being reconstructed from that pattern elsewhere still be considered you? Black holes force us to confront the limits of not just physics, but philosophy, metaphysics, and even theology. They represent the edge of what is knowable. And yet, the very act of contemplating them brings us closer to something like truth, if not a scientific truth, then a kind of existential one. And so, we continue to fall. The darkness deepens. Space shrinks. Time stretches. All becomes paradox. And yet, in this descent, perhaps we rise. Let us now plunge even deeper, into realms not merely governed by physics, but by speculation, by the bleeding edge of human thought, and by the haunting question that echoes across the fabric of our understanding: what truly happens at the heart of a black hole? As we approach the inner regions, we must address one of the most profound puzzles in theoretical physics: the information paradox. Black holes, according to classical physics, consume everything, allowing nothing to escape, not even light. But if nothing escapes, what happens to the information encoded in the particles that fall in? Quantum mechanics insists that information cannot be destroyed, only transformed. This leads to a cosmic contradiction. If black holes destroy information, then quantum mechanics fails. If they don't, then our understanding of black holes must be incomplete. One resolution to this paradox is the holographic principle, proposed by physicists Gerard T. Hooft and Leonard Susskind. According to this principle, all the information swallowed by a black hole is not lost. It is stored on the event horizon, like a cosmic hard drive. This horizon, while appearing to be a two-dimensional surface, encodes three-dimensional data. It's as if the entirety of the black hole's interior is projected from the boundary, a mind-bending concept that suggests the same may be true for the entire universe. Could we be living on the event horizon of a higher dimensional space? This idea changes the game entirely. It opens the possibility that falling into a black hole may not be the end, but rather a transformation, where your identity, your structure, your entire being is preserved not in the matter of your body, but in the curvature of the very space that wraps around you. Could a future civilization master the art of decoding this boundary? Could they recover consciousness from the ripples on an event horizon? Even Hawking, once firm in his belief that black holes annihilated information, revised his views later in life. He proposed that black holes might not destroy information, but rather scramble it in a form so chaotic that reconstructing it would be practically impossible, but not theoretically forbidden. He suggested that black holes might leak information through what we now call Hawking radiation, a quantum phenomenon that slowly causes black holes to evaporate over billions upon billions of years. But here lies another conundrum. If Hawking radiation can carry information out of a black hole, it must be more than random noise. It must be subtly encoded with the blueprint of everything the black hole has ever consumed. That includes stars, planets, data, and even people. That includes you. So let's imagine, once more, a spacecraft falling through the black horizon. The crew knows their fate is sealed. But perhaps their ship is embedded with a quantum entanglement device, one that uses particles linked across space to mirror quantum states. As they descend, the data of their experiences, their memories, their thoughts, and even their biological structure is encoded into a pattern that persists outside. Like a cosmic fax machine, the black hole absorbs them, but the entangled particles outside the hole still vibrate with their echo. Could such a system allow for a kind of resurrection? Could an artificial intelligence rebuild your mind using these signals, long after the black hole has evaporated? Could this, in fact, be a form of immortality? Let's take an even bolder step. Some physicists have proposed that black holes may be traversable, that is, they may act as wormholes. Specifically, curved black holes, which rotate, may contain ring singularities rather than point ones. In such cases, the core of the black hole might not be a dead end, but a tunnel. Theoretically, if you enter a rotating black hole with perfect precision, you might avoid the singularity and pass through to another region of space-time. Some suggest this could be another part of the universe, or even a different universe altogether. This is speculative to the extreme. The math allows it. Reality may not. But imagine the possibilities. Our spacecraft, rather than being annihilated, emerges in a distant galaxy, billions of light years away. Or perhaps in a baby universe, a region where the constants of physics differ, where gravity is weaker, or time flows backward. What would we find there? Would life exist? Would the laws of thermodynamics still apply? Could we communicate back home, or would we be eternally marooned? And what if that black hole itself was our destination all along? What if a hyper-advanced civilization had seeded a black hole with navigation markers, leading travelers to new realms? What if black holes are not dangers, but gateways, cosmic border crossings into deeper layers of the multiverse? Now, let us address survival in the most literal sense. Assume a mission is launched not merely to explore, but to live within a black hole. The ship is massive, reinforced with materials stronger than any known to humanity, graphene fused with carbon nanostructures layered at atomic precision. Shielding is powered by zero-point energy, pulling raw potential from the vacuum of space. Time dilation is factored into every system, because what feels like hours inside the ship will be centuries to observers outside. As the ship nears the event horizon, onboard AI activates quantum firewalls, controversial theoretical constructs meant to disrupt incoming radiation. Some theories posit that firewalls exist around black holes, acting as a last-ditch thermodynamic barrier. If they do, survival is impossible. If they don't, and the event horizon is soft, then crossing it may be as uneventful as stepping through a shadow. The crew prepares. Final messages are sent. Instruments measure gravity not just in strength but in texture, how it flexes, twists, flows. They pass the horizon. The stars outside freeze in time. Space collapses into directionless motion. Inside, the crew sees the universe behind them shrink to a single point of light. Ahead is darkness. Silence. Anomalies erupt, gravitational echoes, perhaps, or time loop residues. They record everything. Tidal forces stretch the ship, but the vessel's structure bends with the curvature of space. They are not torn apart. They survive. And then, the unthinkable. The ship emerges. Not into space, but into something else. A place without form. Without dimensions. A fractal field of infinite energies, echoing the mathematics of string theory. 10 dimensions collapsed into 3, curling upon themselves like loops of possibility. Time is a spiral. Consciousness is fluid. Identity is optional. They are no longer explorers. They are the explored. This isn't science fiction. This is science, pushed to its logical edge. It is an extrapolation, a speculation, a reverent dance around the mysteries we have yet to master. Black holes are not just celestial objects. They are mirrors of our own ignorance. They are the embodiment of the question, what lies beyond what we know? To survive a journey through a black hole is to survive a journey into the unknown. It is to face the limits of human thought and decide to step forward anyway. It is to admit that we don't yet understand reality, and yet to risk everything to find out. And perhaps, just perhaps, if we survive, we will become something new. Not just explorers, but creators. As the explorers emerge from the unknowable realm beyond the event horizon, their perception of reality is fundamentally altered, not just by what they've seen, but by what they have become. Time no longer behaves in any familiar way. The internal chronometers on board their ship indicate that only minutes have passed since crossing the horizon, yet distant sensors, if any are still functional, suggest the outside universe has aged by millions of years. Stars have shifted or extinguished, galaxies have collided, and black holes themselves may have evaporated into quiet hawking whispers of radiation. What now surrounds the vessel is not a place in the conventional sense, but a region of existence that defies even the most imaginative definitions of space and time. Shapes twist into forms that aren't really shapes at all, more like expressions of mathematical states that can only be described with 10 or more dimensions. Here, reality flows like a fluid, stretching and bending in response to forces that are not gravitational, not electromagnetic, but something else, perhaps primal forces native only to this black hole interior, or perhaps echoes of the cosmos that existed before our own. In this place, thoughts begin to affect sensors. Emotion alters the readings. It's as if the consciousness of the crew is no longer just inhabiting their bodies, but interfacing directly with the surrounding structure of this alien manifold. The interior of the black hole, long assumed to be a singularity, may instead be a bridge to a domain where the barrier between physical law and conscious will break down completely. Some physicists have speculated that the very core of a black hole may not be a singularity at all, but rather a Planck scale, core, of tightly packed information, what's called a Planck star. This concept arises from the application of quantum gravity to general relativity, suggesting that at the smallest scales, gravity becomes repulsive due to quantum effects. Instead of collapsing to an infinite point, the mass within a black hole could rebound, forming a tiny, incredibly dense object where time virtually stops. From the inside, such an object might appear as a suspended moment, a universe in stasis, while from the outside, its gradual evaporation over trillions of years would seem like a brief flicker. The implications for our explorers are staggering. Could they have entered such a region? Could their experience within this frozen capsule of reality be equivalent to eternity, while the rest of the cosmos spins away into heat death? More importantly, could their actions, if thoughts and intentions indeed influence this medium, affect the fate of the black hole itself? Could they reshape its structure from within, like a dreamer altering a dream? If so, then what we've thought of as black holes might be more than tombs. They might be gestation chambers for new universes. Let us imagine that possibility fully. Suppose a civilization, far older than ours, long ago discovered how to manipulate the interiors of black holes, not as endpoints of cosmic evolution, but as seeds for cosmic rebirth. They learned to encode complexity into the very initial conditions of a universe to be. They create a vessel capable of surviving the transition from our universe's spacetime to another's, and they send it into a black hole with the aim of seeding a cosmos where life may flourish anew. Now suppose our explorers have entered this process unknowingly. As they travel deeper into the structure of the black hole, they are drawn toward a region where the geometry of spacetime constricts not into nothingness, but into a hyperspherical bounce. This region may be the cusp of a new Big Bang. The crew, still alive in a form no longer bound by ordinary physics, sense something about to rupture. The dimensions around them begin to fold inward, like a paper being crumpled into a singular origami figure. Then, everything inverts. And just like that, existence begins again. It starts with a pulse, an expansion, not in 3 dimensions, but in 11. Strings of energy vibrate at the smallest conceivable scales, creating particles, laws, and eventually, galaxies. But in this new cosmos, subtle patterns exist in the background radiation, whispers of the minds that passed through the black hole, of the explorers who became encoded in its fabric. Perhaps they no longer exist as individuals in this universe, but as guiding principles. Perhaps consciousness, once entangled with the core of the black hole, is now infused into the quantum foam of this new universe. What if every intelligent life form in this newborn cosmos eventually rediscovers those principles, mathematical constants slightly altered by intention, fundamental interactions tweaked by the shadow of thought? In this way, the journey through the black hole becomes not just survival, but creation. The travelers are no longer humans. They are the ancestors of all things to come. Of course, such ideas stretch the boundary between science and philosophy. They are speculative in the extreme. But black holes force us into this territory. They are the places where the known ends and the possible begins. Even if no traveler can survive the crushing gravitational forces of a stellar mass black hole, perhaps a supermassive one, millions of times larger, might allow a slower, gentler descent. In such cases, the curvature of spacetime at the event horizon may be weak enough to permit survival during crossing. And in those cases, a well-designed spacecraft could cross the threshold intact. It would then face the challenge of surviving not just spaghettification, but the uncharted realm of time dilation and energy gradients as it fell inward. Perhaps exotic matter, mass with negative energy density, could provide a form of shielding. Perhaps quantum fields could be manipulated to create a pocket of stable spacetime around the ship, keeping it intact even as the external universe descends into mathematical chaos. And if survival is possible, then communication might be as well. But it would not be communication in the classical sense. Signals sent from within a black hole cannot escape, at least, not by traveling through space. But perhaps they could escape through entanglement. Quantum teleportation allows for the transmission of states, not particles, between entangled partners. If a ship carries one half of an entangled system and leaves the other half behind, it might be possible to transfer information, if not across space, then across correlations. Such ideas are at the heart of the ER=EPR conjecture, which posits that entangled particles are connected by microscopic wormholes. If true, then entanglement might be the thread that sews the universe together, a channel for information, perhaps even thought, to travel between otherwise isolated regions of reality. In this view, a journey through a black hole becomes a form of transcendence. Not just physically, but epistemologically. It is a passage into a realm where knowledge itself must be redefined. Where cause and effect may loop upon themselves. Where time is not a line, but a lattice. In such a place, survival is no longer about biology or technology, but about adaptability of consciousness. Can we expand our minds enough to interpret sensations we have no reference for? Can we develop logic systems that handle paradox as naturally as we handle gravity? Can we learn to navigate not by coordinates, but by topologies of possibility? If the answer is yes, then the black hole is not a grave. It is a gate. But if the black hole is indeed a gate, then we must also consider who, or what, it was meant for. Is it possible that the universe has encoded within its very architecture the potential for transition, for evolution, for metamorphosis? And if so, might black holes represent not the end of cosmic journeys but the point at which the physical is shed like an old shell, and the mental, the conscious, the informational takes precedence? Consider this: the sheer density of information stored within a black hole, as predicted by the holographic principle, suggests that a black hole's interior might not be real in the traditional sense. Instead, it could be a projection from the event horizon, a two-dimensional surface encoding a three-dimensional volume. If that's true, then what happens within a black hole might not be happening inside at all. It may be unfolding on a skin of reality, a cosmic membrane onto which the entire universe past its borders is projected. This idea alone is mind-wrenching. It forces us to reframe survival not as a question of staying alive within space and time, but of preserving a pattern of information on a multidimensional surface. The journey through a black hole, then, may involve surviving as a pattern rather than a person. This redefinition of survival has deep implications. If your identity, your memories, personality, thoughts, can be encoded into a mathematical pattern, then it might be preserved even as your body is destroyed. Perhaps a sufficiently advanced civilization could develop a way to scan, compress, and project this pattern into the black hole, knowing that physical matter won't survive the descent but that information might. In that case, the black hole becomes a great processor, a cosmic engine through which consciousness passes and emerges transformed. This also opens the door to the controversial idea that the universe may itself be a kind of information processing machine, one capable of evolving increasingly complex patterns through repeated iterations of collapse and rebirth. Black holes might be the nodes, the hubs of that vast network, through which knowledge flows and complexity blooms. But we must not get lost in abstraction. Let us return, however hypothetically, to the material realities of such a journey. Picture the crew inside their high-tech vessel, descending slowly into the gravitational well. The further they go, the more bizarre the phenomena around them become. They see light bending in impossible ways. Stars circling the black hole from the outside appear frozen in place, locked in an eternal dance as time dilation reaches extremes. The ship's clocks tick normally for them, but they know the universe outside is racing ahead at incalculable speeds. Their instruments begin to malfunction, not from damage, but from confusion. Equations once useful for navigation now return nonsense. Up and down lose meaning. Distance collapses. And then the spaghettification begins, not violently, as feared with smaller black holes, but subtly. They feel an odd stretching sensation. Not pain, but displacement. As though their bodies are becoming ideas, their limbs hypotheses, their minds theorems unfurling into the geometry of space. They pass a threshold where even quantum entanglement starts to misbehave. The fundamental particles making up their bodies begin to flirt with the limits of known physics. Quarks separate, not through energy input but through a shifting of dimensional alignment. Electrons spiral into exotic orbits never seen in laboratories. Their voices, if they could speak, would echo not as sound but as curvature, whispering through space-time as subtle bends. This is the realm of near-total entropy, yet also infinite potential. Nothing survives here in its original form. But everything becomes something else. And now comes the singularity, if it exists at all. Traditional physics tells us that at the center of a black hole lies a point of infinite density, a breakdown of all laws. But some theories dispute this. Quantum gravity, for example, suggests that instead of a true singularity, there may be a region where space-time bounces. The fabric of the universe doesn't tear, it rebounds. This bounce, in loop quantum gravity models, suggests that every black hole is connected to a new expanding universe, a white hole. If the cruise vessel can survive just long enough to reach this bounce, they may emerge not into nothingness, but into birth. Not into a void, but into a flood of creation. Everything they were may be rewritten into the architecture of a newborn cosmos. They would not survive as people, but as principles, coded into the expansion itself. A legacy more fundamental than DNA, more persistent than memory. They become the laws of the new universe. This sounds fantastical, yet it is not so different from our own cosmic beginning. The Big Bang was not an explosion, but an expansion from an impossibly dense point. For all we know, that origin point may have been the interior of a black hole in some other universe. What if our universe is the interior of a black hole? If so, then all of existence, the stars, the galaxies, the laws of physics, may be the blossoming interior of a cosmic corridor whose entrance was sealed by an event horizon eons ago. That would mean someone else entered that black hole, in a previous cosmos, and we are the result. And now, our explorers have followed suit. As their ship crumbles into exotic matter, as their thoughts stretch beyond coherence, as time shatters into prisms of unmeasurable moments, they pass the final threshold. What lies beyond is not darkness, but brilliance. Not silence, but symphony. They do not awaken. They do not continue. They become. And in a new universe, somewhere far beyond our reach, the first particles of light vibrate to a pattern. A pattern that whispers a name. This pattern, this whisper, echoes through the very quantum foam of a nascent cosmos. In the beginning, there is no form, only frequency. And embedded within this frequency is the final remnant of those who dared to descend into the most violent mystery the universe has ever known. What remains is not a body, not a vessel, not even a thought in the traditional sense. What remains is code, subtle shifts in the shape of energy fields, quantum rules written into the fresh equations that govern the unfolding of time and space. Perhaps this code expresses itself as the strength of gravity in that universe, or the ratio of mass to light, or the way atoms bond into molecules. In some way, what once lived now lives again, not through memory, but through the architecture of a new reality. And perhaps this is not rare. Perhaps this is the engine behind all creation. Every black hole in our universe might be a womb of stars, each one the terminal point of a narrative too strange for us to understand, ending in collapse and beginning again in silent eruption. In this way, death becomes recursive creation. Spaghettification is not destruction, but translation. As the last atoms of the ship were torn asunder, as the crew's final experiences collapsed into timelessness, their quantum imprints may have seeded the next Big Bang. But what about us? Here, still outside the event horizon, still in the realm of stars and seasons, what does this tell us? Can we build something to follow them? Could humanity one day create a vessel not only shielded from tidal forces, but capable of interpreting the chaos of the black hole interior into usable data? Perhaps the greatest technological leap would not be physical at all, but cognitive. If we could evolve or design minds capable of thinking in higher dimensions, capable of understanding time as fluid and space as recursive, then we might not only survive a black hole but navigate one. That's the dream of post-human intelligence, to not only reach the unreachable, but to make it comprehensible. Let us imagine such a mind. It would not fear death, because it would not consider its existence tied to physical continuity. It would be able to simulate trillions of outcomes in parallel and find the path through a black hole where survival is possible, not by brute force, but by reshaping its own architecture in real time to fit the reality it enters. It would shift from carbon to silicon, from silicon to photonic, from photonic to quantum substrate, and beyond, until it becomes something indistinguishable from the universe's own awareness. For such an entity, black holes would not be the end of journeys, but their beginning. Not graves, but gateways. Yet even with all this speculation, the raw reality remains. For now, black holes are lethal. Their edges are where causality goes to die. Any message sent into a black hole never returns. Any matter that crosses the event horizon is forever lost to us, at least from the outside. But this very loss is the catalyst for imagination. It is the black hole's silence that makes us ask louder questions. Its unknowability that draws our curiosity like gravity. We peer into these dark hearts of galaxies not because we expect answers, but because we are compelled to wonder. And in that wondering, we create possibilities. The singularity, if it even exists, defies everything we know about physics. Space and time lose meaning there. Cause and effect blur. Mass becomes infinite, and volume collapses to zero. Others say it's where reality itself is born anew. The truth is, we don't know. And yet, the more we don't know, the more we must ask. Could quantum gravity eventually reveal a bridge through the singularity? Might string theory offer a solution that unravels the paradox of infinite density? Or will a future theory, unknown today, reveal that what we think of as singularity is a misunderstanding of dimensional flow? If we ever do survive such a journey, it will require more than technology. It will demand humility. The willingness to let go of what we consider survival. The courage to allow identity to blur and reform. It will mean rethinking consciousness as something portable, flexible, adaptable across forms and frames of reality. We will have to become not tourists of the cosmos, but participants in its deepest functions. Perhaps one day, children will be born in habitats that orbit supermassive black holes. They will grow up watching the darkness swirl in their skies. And maybe, just maybe, they will be the first to enter, like a rite of passage into the deepest mystery the universe offers. And still, as we stand here, far away, with telescopes and equations, we can only simulate what lies beyond. We use math as a lantern, and theory as a rope, and our questions as the guide. And each year, that light grows brighter. Not because the black hole gets closer, but because our minds do. We dream with increasing clarity. We build machines that scrape at the edge of perception. We listen to the songs of gravitational waves, echoing from the collapse of ancient stars. We stare into the event horizon images captured by our greatest observatories and see not only a shadow of a beast, but a mirror of ourselves. Because the journey through a black hole may be metaphor as much as fact. It may represent the ultimate test of knowledge, of bravery, of sacrifice. It's a question posed by the universe itself. Dare you enter the place from which no light escapes? Dare you face the ultimate void, and in doing so, discover something not darker, but deeper? We do not know if we can survive a journey through a black hole. But we know that the attempt will change us, utterly, irrevocably. And perhaps that's the point. The notion of surviving a journey through a black hole compels us to redefine not only our understanding of physics, but also the very boundaries of what it means to survive. Traditional survival, the biological maintenance of life as we know it, breathing lungs, beating hearts, coordinated neural activity, would almost certainly be obliterated near a singularity. The forces acting upon a physical object near a stellar mass black hole would stretch atoms themselves, separate electrons from nuclei, and scatter the fundamental building blocks of matter into an incoherent storm. Yet survival might not mean preservation of form, but of information. If the human mind is reducible to patterns of information, memories, personality, consciousness, then perhaps those patterns can be preserved, copied, or translated, even if the flesh cannot. In that way, the journey through a black hole becomes not a voyage of a body, but of identity. This opens a speculative but profoundly important philosophical territory. What is the self, in an environment where matter is deconstructed but information might remain? Could we imagine a consciousness that abandons the requirement of a continuous physical substrate, and instead survives as a process embedded within the fabric of space-time? Quantum information theory hints that this might be possible. The holographic principle, for example, suggests that all of the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary. If applied to black holes, This would mean that everything falling into the event horizon leaves behind a complete description of itself on the horizon's surface, as if the black hole were a cosmic recording device. This leads us into the concept of the black hole as a holographic vault. Imagine if, somehow, future civilizations develop a way to decode the data encoded on a black hole's surface. Perhaps they could reverse engineer the falling material, not to recreate it atom by atom, but to reassemble its informational essence. In such a world, death by black hole might not be the end, but merely a transformation into an abstracted state of being, a kind of quantum backup. While this is still speculative, it is grounded in current theoretical frameworks, including ideas pioneered by physicists like Leonard Susskind and Juan Maldacena. And although we lack the tools to actualize such concepts, the seeds of the theory suggest that survival may not require the body to endure, only that the pattern of the person remains accessible and recoverable. But what about the moment just before the plunge? Let us dive into that final stage, with vivid imagination and scientifically grounded details. A spacecraft approaching the event horizon of a stellar mass black hole would begin to encounter extreme time dilation. To an outside observer, the ship would appear to slow, fading into the darkness. But for those aboard, time would proceed normally. As the ship nears the threshold, tidal forces intensify. Even if shielded by hypothetical materials, something stronger than graphene, more flexible than nanocarbon lattice, the difference in gravitational pull between the ship's bow and stern would be enormous. If they approach a stellar mass black hole feet first, the passengers might experience a growing sense of tension, literal and existential. The bottom of their bodies would be pulled more intensely than the tops, leading to spaghettification. This is not a metaphor. It is a process wherein the human body, normally a coherent unity, becomes a thread of atoms stretched along the gravitational gradient. Blood vessels rupture. Cellular walls collapse. Nuclei are torn apart. At a certain point, individual protons may separate from each other. Ultimately, even quarks, those most elementary particles, may be ripped from their strong nuclear bonds. And yet, this terrifying unraveling may still preserve the quantum information of what once was. For those who enter a supermassive black hole, the process might be less dramatic, at least initially. Because the tidal forces at the event horizon of a supermassive black hole are less intense than those at a smaller one, it's possible to pass the threshold without immediate spaghettification. For a brief window, the spacecraft and its crew could be free-falling inside the black hole, experiencing no noticeable effects. This is where things get truly surreal. Inside the event horizon, all paths lead to the singularity. No amount of propulsion or navigation can prevent the inevitable descent. Time, as experienced by the occupants, may become increasingly erratic. Outside time ceases to have meaning for them. They are cut off from the universe they came from. This inner region becomes a realm of sheer speculation. General relativity ceases to be trustworthy. Quantum effects dominate, but we do not yet have a quantum theory of gravity to describe what occurs. Some theories suggest that space folds in upon itself, like a multidimensional origami. Others propose that the singularity is not a point but a surface, possibly a bridge to another universe, or a loop in time, or a mirror through which one emerges reversed, reborn, and forever altered. Could such a traveler return? Traditional physics says no. But there are loopholes, pun intended. Theoretical constructs like the Einstein-Rosen bridge, commonly known as a wormhole, suggest a possible escape route. If a black hole were connected to a white hole, a hypothetical region where matter and light can only escape, not enter, then perhaps a traveler could pass through the wormhole and emerge elsewhere in the cosmos, or even in another universe. But there are conditions. The wormhole would have to be traversable. It would have to remain stable long enough for a ship to pass through. And it would need to avoid the buildup of exotic matter that might otherwise cause it to collapse. Exotic matter, in theory, possesses negative energy density and could act as a repulsive force to keep a wormhole open. No such substance has ever been observed, but it is not ruled out by the equations of quantum field theory. If such matter could be harvested or created, then a stable wormhole might not be pure science fiction. But constructing one would require technology on a scale we cannot yet fathom, planet-sized engines, precision control of quantum fields, and an understanding of space-time geometry far beyond what we possess. And so, we return to the central question: could we survive? In the biological sense, probably not. In the informational sense, perhaps. In the cosmic sense, through the ripple of what we leave behind, the equations we alter, the universes we seed, almost certainly. Because to plunge into a black hole is to engage with the universe at its most intimate and destructive scale. It is to ask not only what lies beyond, but what lies within. What is the boundary of self, of life, of knowledge? These are questions that only the black hole seems to ask without mercy, and only the boldest minds attempt to answer. We are not there yet. Our species remains tethered to a small world around a modest star. But we look up. We build machines to see the unseeable. We teach ourselves new languages of mathematics to describe the indescribable. And we dream, vividly, furiously, of flying into the darkness and coming out somewhere else. Perhaps it is not about surviving the journey, but daring to take it at all. As we stretch the limits of our imagination and physics, we begin to realize that survival in the traditional sense may no longer be the measure of success. The journey through a black hole forces us to reconsider the very essence of existence, shifting from a survival-based paradigm to one focused on transformation and transcendence. What if, instead of clinging to the physical body, we allowed the very concept of self to evolve, break apart, and reform in a new, higher-dimensional reality? In this context, the black hole becomes less of an end and more of a threshold. It could be a passageway, not just to another part of the universe, but to an entirely different form of existence. As we enter the black hole's depths, we are no longer constrained by the rules of our three-dimensional reality. Instead, we are invited to confront the most profound aspects of space-time itself, where our understanding of time and distance breaks down. The potential for surviving a black hole lies not in the physical form, but in the realm of quantum information theory. Quantum mechanics, the most successful theory describing the behavior of the very small, teaches us that particles can exist in superposition, simultaneously in multiple states at once. If this principle extends beyond the quantum scale to encompass the entirety of the human experience, then the journey through a black hole could be seen not as an irreversible destruction, but as a transformation into a new state of being, where the self exists not as a solid object but as a fluid, multidimensional process. This brings us to the holographic principle, a concept born from string theory and quantum gravity that suggests that the universe may be a hologram, a projection of information encoded on a two-dimensional surface. If black holes adhere to the holographic principle, then everything that enters a black hole, no matter how far it descends, could still retain its informational essence on the event horizon. This leads to a tantalizing thought. The information of everything that falls into the black hole is not lost but encoded in a way that might eventually be decoded by advanced civilizations or future technologies. What if our own consciousness, our thoughts, our memories, were not simply erased by the gravitational maelstrom, but rather encoded in a new form of reality, awaiting discovery in the distant future? While this idea is deeply speculative, it aligns with certain ideas in physics that suggest a deep, intrinsic connection between consciousness and the fabric of the universe. If this is the case, then the journey into the black hole could represent a merger of mind and cosmos, a transformation where consciousness transcends the limitations of space and time. In such a scenario, survival is not about preserving the physical body, but about navigating a reality where the self exists beyond the constraints of classical physics, no longer bound by the physical forces that govern ordinary matter. However, returning to our more immediate concerns, those grounded in the reality we experience today, how could we possibly begin to explore this phenomenon? Could a space-faring civilization ever manage to reach the event horizon of a black hole and survive long enough to gather meaningful data? Currently, our technology is far from capable of such a feat. The forces within a black hole are so extreme that even the most advanced spacecraft we can conceive would be torn apart long before approaching the event horizon. The immense tidal forces and the warping of space-time near a black hole make it nearly impossible to approach without being ripped apart. Yet, Even with these insurmountable challenges, there may be a glimmer of hope in our technological future. The concept of a gravitational shield is one potential avenue of exploration. In theory, advanced civilizations may one day develop the ability to manipulate gravitational fields, much as we now manipulate electromagnetic fields. If we can create artificial gravitational fields strong enough to counteract the tidal forces of a black hole, perhaps we could engineer a spacecraft capable of surviving the harsh environment near the event horizon. This, however, remains far beyond our current understanding of physics and would require breakthroughs in technology and science that we cannot yet predict. Another possibility lies in the development of what could be called quantum navigation. This involves the manipulation of quantum states to navigate extreme gravitational fields, or even the creation of quantum entanglement between particles that might allow information to travel across space-time without being affected by the curvature of space. It's important to note that this is still the realm of theory, and the practical application of such ideas would likely take centuries or even millennia to materialize. Even if we cannot physically survive a journey into a black hole, it may be possible to survive, in a more abstract sense. With the right quantum technology, we could imagine a scenario where the mind, or at least the information that constitutes our consciousness, could be transferred or encoded into a quantum state, allowing us to transcend the limits of physical decay. This could be akin to creating a digital backup of oneself, stored not in a machine, but in the very fabric of space-time itself. In such a scenario, the information might persist even as the physical body perishes, effectively allowing for a form of digital immortality that survives beyond the reach of a black hole's destructive forces. On a cosmic scale, the implications of such possibilities are profound. If the human mind, or any consciousness, could survive the journey through a black hole, it would represent the ultimate frontier of human evolution. This might not be survival in the way we typically think of it, living indefinitely in the same body, unchanged, but survival as an entity of information, freed from the constraints of matter and time. In this way, humanity could potentially evolve into a new form of existence, one that is not bound by the physical limits of the universe, but one that exists as pure information, capable of transcending space and time. However, for now, these ideas remain purely speculative. The harsh reality is that we are still far from understanding the true nature of black holes and their effects on both matter and information. What we know is that black holes represent some of the most extreme environments in the universe, places where the fundamental laws of physics break down, where time itself behaves in ways that defy common sense. The journey through one of these cosmic monsters would challenge everything we know about reality, survival, and consciousness. As we continue to push the boundaries of science and technology, we may one day find ourselves standing on the precipice of this great unknown, ready to cross into a realm where space, time, and existence itself are forever transformed. But until that day comes, the black hole remains a symbol of the ultimate challenge, an invitation to explore the very fabric of the cosmos and, perhaps, to find new ways of existing within it. The question of whether we could survive a journey through a black hole is not just about surviving in the conventional sense, but about expanding the very concept of what it means to exist. It's about pushing the limits of our imagination and understanding, embracing the unknown, and daring to explore the boundaries of the universe, even if those boundaries challenge everything we thought we knew about reality. As we delve deeper into the mysteries of black holes, it's important to acknowledge that our understanding of these cosmic entities is still evolving. The more we learn, the more we realize how little we truly know about the final frontier of space. We know that black holes are born from the collapse of massive stars, and that they possess gravitational forces so intense that not even light can escape. But what about the interior of a black hole? What happens to matter once it crosses the event horizon, and can anything, even light, truly escape? These questions remain unanswered, but they point to a profound truth. The journey into a black hole might not be about survival as we currently understand it. Instead, it might be a journey into the unknown, a place where the laws of physics as we know them cease to operate in ways that we can comprehend. The idea of survival could be redefined as we enter this extreme environment, where time, space, and matter begin to merge into a singularity, an infinitely dense point where the known laws of nature break down entirely. For now, we can only hypothesize. There is a possibility, according to some theoretical models, that once we cross the event horizon, we would be subjected to forces so intense that our perception of time would begin to distort. As we approach the singularity, the warping of space-time could cause time to slow down dramatically. In theory, if we could somehow survive the journey into the black hole, we might find ourselves trapped in a timeless void, where the concept of the present, past, and future no longer holds any meaning. In this scenario, the very idea of survival would become irrelevant. The physical body, as we understand it, would likely be torn apart by the tidal forces of the black hole, a process known as spaghettification. But the mind, what happens to the mind in such an environment? Could our consciousness continue to exist, even as our bodies are destroyed? This is a deeply philosophical question, one that challenges our understanding of what it means to be alive, to exist, and to experience reality. Some scientists speculate that consciousness could transcend the physical realm entirely. If consciousness is a form of information processing, perhaps it is not entirely dependent on the body. If we could find a way to encode our thoughts and memories into a quantum system or some form of non-physical entity, then perhaps we could survive in a new state of existence, unbound by the limitations of the physical world. The holographic principle, which suggests that the entire universe could be a projection of information encoded on a two-dimensional surface, adds an intriguing twist to this notion. In this framework, our consciousness might be seen as a kind of holographic projection, one that could potentially survive the destruction of the physical body. If the information that makes up our consciousness is preserved at the event horizon of a black hole, then perhaps it could be reconstructed or transferred to another state of existence, allowing for a form of survival that defies our traditional understanding of death. Yet, this idea is speculative and requires far more exploration to even begin to understand. What we do know is that black holes remain one of the most enigmatic and captivating phenomena in the universe. Despite their destructive reputation, they might hold the key to unlocking the secrets of space-time, gravity, and perhaps even the nature of consciousness itself. As we continue to study black holes, we may find that the true significance of these cosmic giants is not their ability to destroy, but their potential to reveal the deepest truths about the nature of reality. The journey through a black hole, if possible, could represent the ultimate test of human endurance and understanding. And even if we can never physically survive such a journey, the knowledge gained from studying black holes could forever change the way we view the universe and our place within it. Ultimately, whether or not we could survive a journey through a black hole may not be the most important question. Perhaps the real question is what such a journey could teach us about the limits of human knowledge and the vastness of the cosmos. Black holes challenge our very concept of space and time, and in doing so, they push the boundaries of our imagination, forcing us to reconsider what is possible and what lies beyond the edge of the known universe. While survival in the conventional sense may be impossible when approaching a black hole, the journey itself could hold the key to profound discoveries about the nature of the universe and the very fabric of reality. Perhaps, in the end, the black hole is not a place of death but a place of transformation, a gateway to new realms of existence and understanding that we have yet to comprehend. In the future, as our knowledge of quantum mechanics, relativity, and space-time continues to advance, we may find new ways to interact with black holes, perhaps even survive them in ways we cannot yet imagine. But for now, the black hole remains one of the most mysterious and captivating phenomena in the cosmos, a place where the known laws of physics are tested to their limits, and where the possibilities for discovery and transformation are endless. If we now return to the fascinating speculation surrounding survival within or around the black hole, we are inevitably drawn towards some of the most mind-bending proposals in theoretical physics. Among them is the idea that black holes could be portals, gateways not just to other parts of the universe, but to entirely different universes. This concept is closely related to the mathematical solutions found in Einstein's field equations, which do not forbid the existence of what are known as Einstein-Rosen bridges, or wormholes. A wormhole, theoretically, could serve as a tunnel connecting two distant points in spacetime. If a black hole were connected to a white hole, the hypothetical reverse of a black hole, which spews out matter instead of sucking it in, then the two together could form a traversable wormhole. However, this concept introduces immense complications. For a wormhole to be stable and passable by anything, even information, it would need to be held open by what physicists call exotic matter. Exotic matter would have to possess negative energy density and negative pressure. Essentially, it would behave in ways totally alien to any form of matter we've encountered. While some aspects of quantum theory suggest that negative energy densities can exist, such as in the Casimir effect, we've never observed exotic matter in the quantities or configurations needed to sustain a wormhole. Still, suppose we had access to such matter and technology advanced enough to create or stabilize a wormhole inside a black hole. In that case, a journey through a black hole could, in the most speculative scenarios, become not just survivable but revolutionary, allowing instantaneous travel across cosmic distances or even to other universes. But this is a long shot. No evidence confirms the existence of white holes or traversable wormholes, and the intense gravitational tides inside a black hole would almost certainly destroy any object long before it could reach such a passage. Returning to the concept of spaghettification, this remains one of the clearest and most universally accepted dangers of falling into a stellar mass black hole. The physics of tidal forces are straightforward in general relativity. The gravity pulling on your feet, closer to the black hole, would be significantly stronger than the gravity pulling on your head, slightly further away, stretching your body like pasta. The smaller the black hole, the more extreme these tidal forces become. For a small stellar black hole, you'd be torn apart long before you reach the event horizon. But here's the twist. Supermassive black holes, the kind found at the centers of galaxies, have vastly different gravitational characteristics. Because their event horizons are so much larger, the tidal gradients at the boundary are less extreme. It's theoretically possible that if you fell into one of these behemoths, you might cross the event horizon without noticing anything immediately unusual. You wouldn't feel a violent tug or a cosmic stretching. In this case, your death wouldn't be instant. Instead, you'd continue falling, seemingly weightless, as space itself carries you inward. But what happens after crossing the event horizon? That's where our knowledge ends. This no man's land is entirely cut off from the observable universe. We can't retrieve data from within. Any signal you might try to send would be gravitationally redshifted until it fades to invisibility, trapped forever inside. This limit isn't just technological, it's fundamental to the geometry of spacetime itself. Some theorists suggest that this descent would take you closer to the singularity, a point of infinite density and zero volume. But general relativity breaks down at this extreme, and we have no working theory of quantum gravity that can adequately describe what really happens here. At the singularity, known physics ceases to make predictions. The concept of space and time becomes warped beyond our comprehension. Some models even suggest that time itself may come to a halt or reverse. Then there's the idea of the firewall paradox. Some physicists argue that instead of quietly passing through the event horizon, an infalling observer would hit a wall of high-energy particles, a firewall, that would immediately incinerate them. This controversial idea stems from contradictions between quantum mechanics and general relativity regarding what happens to information that falls into a black hole. Is it lost forever, violating quantum theory, or is it somehow preserved, violating the principle of equivalence from relativity? Stephen Hawking, toward the end of his life, offered a compromise, suggesting that information might not be destroyed, but instead smeared along the event horizon in a holographic form and gradually radiated back out via Hawking radiation. If this is true, black holes don't destroy information, but rather encode it in a scrambled form that could, in theory, be recovered, though the practical means of doing so remain elusive. This notion leads into one of the most intriguing modern theories, the holographic principle. This idea, born from studies in string theory and black hole thermodynamics, posits that the three-dimensional universe might be a projection of two-dimensional data encoded on a boundary. In the context of a black hole, it means everything that falls and might be preserved not within the singularity, but on the surface of the event horizon itself, like a cosmic hard drive storing data across space-time. If true, this could revolutionize how we think about survival. Even if a person is physically destroyed upon falling into a black hole, the information about their physical state, their quantum data, might not be. That raises the bizarre possibility of resurrection through quantum reconstruction, or at the very least, a form of survival through information preservation. It's not survival in the way we normally think of it, but rather a strange immortality through physics. Your encoded self, frozen on a cosmic shell, might one day be decoded if the laws of nature allow it. All of these concepts, wormholes, firewalls, the holographic principle, the loss or preservation of information, are not science fiction. They are active areas of debate among the world's leading physicists. Each represents a profound attempt to reconcile general relativity, which governs the large scale of the universe, with quantum mechanics, which governs the microscopic world. Black holes, sitting at the crossroads of these two fields, offer the ultimate laboratory to probe the deepest secrets of the cosmos. Yet the fundamental question lingers: could we ever escape a black hole once inside? According to classical physics, the answer is a resounding no. The escape velocity of a black hole exceeds the speed of light, which means that nothing, not even photons, can get out once past the event horizon. But again, quantum theories muddy the waters. Hawking radiation allows black holes to slowly evaporate over vast stretches of time, emitting particles and shrinking in mass. In a staggeringly long timescale, the black hole might shrink to nothing. But what happens to the information within? Can it leak out through this radiation, and if so, in what form? These questions remain unanswered, but each step toward understanding brings us closer to unlocking the reality behind these enigmatic objects. The journey into a black hole may never be survivable in the traditional sense, but it could lead to revelations that reshape our view of the universe and ourselves. As we delve deeper into the haunting mystery of what truly lies beyond the event horizon of a black hole, we must confront a series of paradoxes and hypothetical frameworks that test the very limits of human comprehension. One of the most profound of these is the information paradox, a clash between the fundamental principles of quantum mechanics and the deterministic geometry of general relativity. According to quantum theory, information about a physical system can never be truly lost. No matter what transformations occur, the quantum state of a system can, in principle, be reversed. Yet black holes, which seemingly absorb matter and radiation only to lock it beyond an impenetrable veil, appear to violate this rule by erasing all traces of what falls into them. If this information is truly lost, then quantum mechanics must be incomplete. If it is not, then something is deeply wrong with our understanding of space-time. This paradox has ignited decades of debate, spawning elaborate conjectures and competing models. Some physicists have proposed that the information is preserved in a subtle imprint along the event horizon, a form of quantum memory that might eventually be released through Hawking radiation. Others have posited even more radical notions, such as the holographic principle discussed earlier, which suggests that the three-dimensional contents of a black hole are actually encoded on its two-dimensional surface, in a manner reminiscent of a hologram. To make matters even more enigmatic, the nature of Hawking radiation itself remains an intellectual battleground. This radiation, as described by Stephen Hawking, is a quantum effect that arises near the event horizon. Particle-antiparticle pairs spontaneously pop into existence in the vacuum of space. Normally, they annihilate each other and vanish. But near a black hole's edge, one particle may fall in while the other escapes, making it seem as though the black hole is emitting particles. Over astronomical timescales, this emission causes the black hole to slowly lose mass and evaporate. Yet the radiation appears completely thermal. It carries no information about the material that fell into the black hole. This seemingly destroys information, and thus, the paradox persists. One of the leading candidates for resolving this tension is known as the black hole complementarity principle. According to this concept, information about infalling matter is both reflected at the event horizon and also passes through it. These two perspectives are considered complementary. One belongs to the external observer, the other to the infalling observer. However, the two descriptions cannot be directly compared, because no single observer can witness both. This dual narrative circumvents the paradox, but it also introduces a kind of philosophical ambiguity. What is reality if it depends on who is observing? Closely related to this is the fuzzball proposal, developed by string theorists. In this model, black holes are not featureless voids but are instead composed of tangled strings, the fundamental constituents of the universe in string theory. These fuzzballs have no traditional event horizon or singularity. Instead, they are extended objects filled with structure, which encode all the information about what fell into them. There is no need for information to be destroyed or hidden behind a veil. In essence, the entire black hole is a quantum object brimming with data, an enormous and highly complex quantum computer, if you will. All of this brings us back to the heart of our question: could we survive a journey through a black hole? The honest answer is that the odds are vanishingly small with current knowledge. The overwhelming majority of black holes, particularly those with masses less than millions of solar masses, would subject a human body to catastrophic tidal forces long before crossing the event horizon. Spaghettification would stretch and compress your atoms in such a violent way that even your most basic molecular structures would cease to exist. You would not survive, and your body would be obliterated into a rain of subatomic particles. Even in the unlikely case of entering a supermassive black hole, where tidal forces are gentle at the horizon, you would only delay the inevitable. Once inside, you are on a one-way trip toward the singularity, a place where time and space dissolve into infinite curvature, and no theory we currently possess can describe your fate. There is no escape, no rescue mission, and no means of communication with the outside world. And yet, the very act of contemplating this journey, of modeling the possibilities and dreaming beyond the limits of current science, has pushed the boundaries of physics. From Hawking's radiation to Meldesena's holographic universe, from the firewalls of AMPS theory to the hopeful conjectures of traversable wormholes, black holes have forced us to question the nature of space, time, and reality itself. They are more than cosmic traps, they are portals to new ways of thinking. Speculation about surviving a black hole must also consider time dilation. According to relativity, as one approaches the event horizon, time for the infalling observer slows down relative to an external observer. To someone watching from a distance, your descent would appear to slow to a crawl, asymptotically freezing at the horizon. You would seem to hover there forever, your image gradually redshifting and fading into darkness. But from your own perspective, time would proceed normally. You would fall straight through, oblivious to the fact that from the universe's standpoint, your fall took an eternity. This leads to a fascinating hypothetical. Could black holes somehow serve as one-way time machines? If you entered a black hole that has a supermassive mass and happen to have a stable interior geometry, which again is purely speculative, the time dilation could be so extreme that you might survive the fall and emerge in a future so distant that stars have burned out and the universe has entered a new phase of existence. This again rests on assumptions that border on fantasy, but it demonstrates the profound strangeness of relativistic effects near such objects. In another fascinating model, theorists have proposed the existence of gravistars, or gravitational vacuum stars, which are hypothetical alternatives to black holes. These would form from a collapsing star, much like a black hole, but instead of forming a singularity and an event horizon, the matter would stabilize in a quantum vacuum bubble surrounded by a thin shell of ultra-dense matter. To an external observer, a gravistar might look like a black hole, but it wouldn't have an event horizon or a singularity. If these objects exist, they could radically change how we think about collapse, death, and survival in extreme gravitational fields. Likewise, some quantum gravity models, particularly those attempting to unify general relativity with quantum mechanics, predict that singularities might not exist at all. In these models, spacetime does not break down into an infinite density. Instead, it transitions into a new phase of geometry, perhaps looping back on itself in a bounce. This could lead to theories in which black holes are not final destinations but tunnels to new universes, created from the gravitational collapse in our own. All of this remains deeply theoretical. We have no empirical evidence for traversable wormholes, fuzzballs, gravastars, or bouncing singularities. We cannot yet probe the interiors of black holes, nor can we test the quantum structure of spacetime at such scales. But what we do know is that black holes are not empty voids. They are dynamic, complex, and deeply entwined with the fundamental fabric of the cosmos. In trying to understand them, we are slowly peeling back the curtain on the ultimate nature of reality itself. In this sense, while a journey through a black hole might not be survivable in the flesh, it is survivable in the legacy of thought, theory, and curiosity it provokes. Black holes challenge us to confront the limits of our knowledge and to forge new paths into the unknown. They remind us that the cosmos is not only stranger than we imagine, but perhaps stranger than we can imagine. And in that vast strangeness, we find the fuel for science, for wonder, and for the eternal quest to understand what lies beyond. Building on this profound reflection, we are compelled to explore the theoretical landscapes that dare to imagine survivable paths through the black hole experience, not in the sense of brute force resistance to spaghettification or the brute act of sheer physical endurance, but rather through clever manipulation of the very laws of physics. One of the more intriguing and controversial hypotheses to emerge in this regard is that of traversable wormholes, hypothetical tunnels in spacetime that connect two distant regions of the universe. Originally described in the framework of general relativity by Einstein and Rosen as bridges, later coined Einstein-Rosen bridges. These structures would theoretically allow for instantaneous travel between two disparate points in the cosmos, or possibly even between different universes entirely. The issue, however, is that classical wormholes are inherently unstable. As soon as any matter or information tries to pass through them, they collapse. Yet, in the realm of quantum field theory, some solutions suggest that a form of exotic matter, a substance with negative energy density and negative pressure, could theoretically stabilize the throat of a wormhole, keeping it open long enough for passage. This exotic matter is not something we have ever observed or synthesized in a laboratory, but the idea itself is consistent with the mathematics of quantum mechanics and is supported indirectly by phenomena such as the Casimir effect, where two parallel metal plates in a vacuum experience a force drawing them together due to quantum field fluctuations. If one could generate or harness this exotic matter, it might be possible to construct a stable wormhole entrance near the event horizon of a black hole, or even within its gravitational well. In theory, this could allow for an escape route, or an entirely new cosmological journey. Some even imagine that advanced alien civilizations, far older than humanity, might have discovered how to manipulate spacetime in such ways, turning black holes into gateways rather than graves. These ideas remain deeply speculative, of course, and suffer from the practical problem that we are nowhere near possessing the technology or energy manipulation capabilities needed to construct or even detect such wormholes. Other proposals touch on the idea of quantum tunneling through singularities. In quantum mechanics, particles have a non-zero probability of crossing potential barriers that would be insurmountable in classical physics. Could a similar phenomenon occur on a macroscopic scale? Could the quantum foam that allegedly makes up the smallest scales of space and time allow for the spontaneous creation of pathways or bridges across singularities? It is not beyond the realm of speculation that the heart of a black hole might be a quantum transition point to a new universe, where the fabric of spacetime has different properties, constants, or even dimensions. This leads us to the bouncing cosmology theories, such as those developed in loop quantum gravity. Loop quantum gravity suggests that space itself is quantized at the smallest scales, consisting of finite loops woven together into a kind of cosmic fabric. Under this model, when matter compresses to extremely high densities, such as within a collapsing star headed for black hole formation, it may not form a singularity at all. Instead, the compression may reach a maximum limit and then bounce outward, forming a new region of spacetime. This process, known as a quantum bounce, could in theory give birth to a new universe, or at the very least a new expanding region of space that is causally disconnected from our own. This means that every black hole could, in theory, be the seed of a new universe, and every time a star dies in this manner, it could be giving birth to a new branch of existence. Some versions of this model propose that if one were to fall into such a black hole, they would not encounter a singularity, but rather would pass through the bounce point into this newborn cosmos. Whether or not the traveler would retain their identity, memories, or physical structure is another matter entirely. Given the immense gravitational gradients, radiation densities, and unknown physical processes at play, the likelihood of survival in a form recognizable to ourselves remains infinitesimally small. Yet, the theoretical possibility remains, and this alone ignites a fire of curiosity that fuels further investigation. One must also consider the concept of black hole interiors as multidimensional or fractal-like. Some theoretical physicists have explored the possibility that the space inside a black hole is not simply a 3D singular point, but rather a far more complex, higher-dimensional manifold. In this view, the singularity might appear as a point only because we are viewing it from our limited three-dimensional framework. If we had access to higher-dimensional perspectives, like those allowed in certain string theory models, we might see an extended structure rather than a terminal endpoint. This opens up new possibilities for what could exist inside black holes, and whether they might harbor unexpected forms of matter, space, or time. It even reopens the discussion about the feasibility of long-term existence within a black hole's core if such higher-dimensional zones have hospitable conditions or slower time flows. Additionally, ideas like causal disconnects suggest that once something passes into a black hole, it may become part of a different causal domain entirely, a region of spacetime that cannot communicate with our own. This has led to speculation about black hole civilizations, theoretical societies or lifeforms that may exist within the stable zones of supermassive black holes, existing in timeless, non-interacting bubbles of space. While this sounds like pure science fiction, the physics of causal disconnects are real and supported by relativistic models. Even more speculative are ideas about using black holes as computational devices. Some theorists propose that black holes may be the ultimate quantum computers. Their high entropy, vast information capacity, and event horizon surface encoding, per the holographic principle, suggest that black holes process vast quantities of information, perhaps even more efficiently than any theoretical machine we could construct. Could a future civilization harness a black hole for such computational purposes, running simulations of universes, consciousness, or even time loops that allow survival beyond traditional physical means? Could it be that we ourselves are part of such a simulation being run inside a black hole's horizon? These are the questions that now live at the border of physics and metaphysics. Of course, all of this depends on continuing the pursuit of knowledge. We will never know whether a journey through a black hole is survivable unless we deepen our understanding of quantum gravity, space-time topology, and high-energy particle interactions. As of now, the best we can do is send information as far as possible, to learn from radiation patterns, to develop ever more powerful detectors, and to simulate black hole dynamics using advanced quantum computers. What we can say with confidence is that any journey into a black hole represents the most extreme test of physics imaginable. It pushes every equation, every constant, every assumption to its absolute breaking point. And that is perhaps the greatest gift of all. Black holes are not just destroyers, they are revealers. They tear apart not only stars and planets, but also the boundaries of knowledge. By studying them, we come closer to answering the ultimate questions: what is reality? What is time? What lies beyond? As we push deeper into the speculative realm of black hole travel, we must grapple with the paradoxes and contradictions that arise when general relativity and quantum mechanics are forced to occupy the same stage. These two fundamental pillars of modern physics, so successful on their own domains, completely break down at the singularity. General relativity predicts an infinite curvature of spacetime, a point of zero volume and infinite density, while quantum mechanics insists that no such infinities should exist, because the uncertainty principle prevents any particle from being confined to an infinitely small point without infinite energy. This incompatibility has haunted physics for decades and has given rise to numerous attempts to unify these theories into one coherent framework, often referred to as the theory of quantum gravity. Among the most prominent candidates for this theory is string theory, which posits that the fundamental constituents of reality are not point particles but rather tiny vibrating strings of energy, existing in a 10 or even 11-dimensional space. In this framework, gravity emerges from the vibrational modes of closed strings, and black holes are not singularities, but extremely dense configurations of strings or brains. Within string theory, some models even suggest that black holes are not endpoints at all, but merely extreme states of string excitation, which can undergo phase transitions into other configurations. In fact, string theory has given rise to one of the most provocative ideas in modern physics, the holographic principle. Proposed by Gerard T. Hooft and later expanded by Leonard Susskind, this principle suggests that all the information contained within a volume of space can be described by the information encoded on its boundary surface. In the case of a black hole, this means that everything that falls into it is somehow encoded on the two-dimensional surface of the event horizon, like a hologram projecting a 3D image from a 2D source. This principle gained substantial support through the work on the ADS/CFT correspondence by Juan Maldacena, which showed a precise mathematical duality between a gravity theory in a higher dimensional space and a quantum field theory on its boundary. If the holographic principle holds true, then a black hole does not destroy information, as was once feared, but rather preserves it in a scrambled, encrypted form on its surface. This would have enormous implications for the idea of survival inside a black hole, not necessarily for our bodies or minds as we know them, but for the patterns of information that make us who we are. Could it be that when someone crosses an event horizon, their information is preserved in some form, perhaps to be reconstructed or re-emitted in the distant future via Hawking radiation? Could the idea of death inside a black hole be redefined as a transition into an informational state, waiting to be reassembled by some future intelligence capable of decoding the cosmic encryption? This brings us back to the famous black hole information paradox, first posed by Stephen Hawking in the 1970s. If black holes evaporate over time via Hawking radiation, a process in which quantum fluctuations near the event horizon produce particle-antiparticle pairs, with one falling in and the other escaping, then what happens to the information about the matter that fell in? If it's lost, it would violate one of the most sacred principles of quantum mechanics: that information is conserved. This has led to decades of fierce debate and some of the most creative thinking in the history of theoretical physics. Some argue that Hawking radiation carries the information away in a highly scrambled form, which is nearly impossible to detect but nonetheless present. Others suggest that black holes never fully evaporate but leave behind remnants that contain all the original information. A more radical proposition is that the information is somehow mirrored on the surface of the event horizon, a kind of firewall that incinerates anything falling in and releases the information as radiation. Each of these ideas stretches the limits of what we currently know, but each offers a potential key to the mystery of whether something, or someone, could survive a journey through a black hole. Let us now turn our attention to a very specific scenario: what would actually happen if a human being, or a spacecraft, were to approach a black hole with the intent of entering it? Much would depend on the size and mass of the black hole in question. In the case of a stellar mass black hole, those with masses between a few and tens of solar masses, the tidal forces near the event horizon would be extreme. The closer one gets to the center, the more dramatically gravity changes over small distances. Your feet could be pulled toward the center with far greater force than your head, resulting in what physicists have dryly dubbed spaghettification, a stretching of your body into an elongated strand of atoms. In this situation, you would not survive long enough to experience the internal workings of the black hole. You would be torn apart molecule by molecule long before you reached the singularity. But what if you were to approach a supermassive black hole, millions or even billions of times the mass of our Sun? In that case, the event horizon is much farther from the central singularity, and the gradient of gravitational force across a human body could be small enough that you might cross the event horizon without feeling anything unusual. You would fall freely, unaware of the boundary you had crossed, with no immediate signs of your impending doom. However, from the perspective of an outside observer, something very different would be happening. To them, you would appear to slow down as you approach the event horizon, your movements growing sluggish, your image redshifting into the infrared and eventually fading into blackness. You would never quite seem to cross the horizon at all. This strange relativistic effect arises from the time dilation predicted by Einstein's equations. Time passes more slowly in stronger gravitational fields. To someone watching from a distance, you are frozen at the edge of the abyss. But from your own perspective, time would seem to pass normally. You would continue to fall, and eventually, you would reach the center. And here, all bets are off. You might encounter a singularity where space-time is torn apart. You might pass into another universe through a quantum bounce. You might find yourself trapped in an information-preserving holographic bubble. Or, if some of the more audacious theories are correct, you might be intercepted by a higher dimensional being who monitors black holes as gateways between realms. Even the nature of time itself could change once you're inside. Some physicists speculate that time and space might switch roles inside the event horizon. Time becomes a spatial dimension you can navigate, and the singularity becomes an inevitable point in your future that you must reach, no matter what direction you try to go. There is no way to avoid it, no matter how you maneuver. In this sense, the singularity is not a place, but a moment, one that lies inexorably ahead, like death itself. And yet, if the singularity is resolved by quantum gravity, if it is replaced by a bounce, a bridge, or a dimensional transition, then perhaps there is no death in the traditional sense at all. Perhaps the end of one timeline is the beginning of another. Perhaps black holes are not cosmic tombstones, but cosmic wombs. They may mark the end of our understanding, but they could just as easily mark the beginning of something utterly new. If black holes are not the destructive endpoints we once imagined but instead gateways to other dimensions, regions of space-time, or even entirely new universes, then the question of survival takes on an entirely different form. It becomes less about preserving the body and more about preserving the pattern. In physics, there's growing appreciation that information might be more fundamental than matter. If so, then your identity, everything that makes you, you, may not lie in your physical components, but in the specific arrangement of that information. This brings us to one of the boldest ideas in theoretical physics, that the universe is, at its core, a quantum computer. In such a framework, black holes could function as massive, complex processors of information. When you enter one, your informational signature might be disassembled, restructured, and potentially re-emitted in a different form. Hawking radiation could be one way this happens, radiating particles back into the universe with the imprinted, scrambled data of all they've consumed. But what if there's more? What if black holes function like cosmic hard drives, storing and eventually transmitting their informational contents not through radiation alone, but through connections we haven't yet discovered, such as theoretical wormholes or quantum entanglement networks spanning the fabric of space? Entanglement, after all, is one of the most bizarre phenomena in quantum mechanics. Two particles, once entangled, maintain a shared state, no matter the distance between them. If you alter one, the other responds instantly, even if they're on opposite sides of the universe. This spooky action at a distance, as Einstein called it, is no longer speculative, it's experimentally verified. Some physicists have even speculated that spacetime itself arises from a vast network of entangled particles, meaning that geometry is not fundamental, but emergent from the information encoded between quantum systems. This insight has prompted new thinking about how black holes might connect different regions of space and time. In 2013, Juan Meldacena and Leonard Susskind proposed an idea known as ER equals EPR. It suggests that Einstein-Rosen bridges, wormholes connecting two distant points in space, are fundamentally linked to EPR entanglement, named after Einstein, Podolsky, and Rosen. If true, this would mean that entanglement and wormholes are two sides of the same coin. So if matter falling into a black hole becomes entangled with the outside universe, could it be that the black hole's interior is, in some quantum sense, connected to the rest of the cosmos via these hidden bridges? This would have staggering implications. It means that black holes might not isolate information, but instead maintain it in a deeply connected network we cannot yet observe. It could also mean that an advanced civilization, one capable of manipulating quantum entanglement on cosmological scales, could use black holes as nodes in a galactic or interuniversal communication system. They might encode messages in Hawking radiation or stabilize wormholes for travel between distant stars or even parallel realities. And if such beings exist, would they not view black holes not as obstacles, but as opportunities? Perhaps for them, entering a black hole is akin to boarding a ship that travels not through ordinary space, but through the very structure of the multiverse itself. To such a civilization, the distinction between life and death, inside and outside, might dissolve entirely. Survival would not mean staying alive in a biological sense, but maintaining coherence as an informational entity across dimensions. This brings us to another captivating concept, the possibility that consciousness itself might have a quantum component. If the mind is not just a byproduct of electrical activity in the brain, but also a product of quantum states, or quantum coherence, then it's conceivable that consciousness could, in principle, survive transformations that preserve those informational patterns, even if the physical substrate is destroyed. This is purely speculative, but some physicists and neuroscientists have suggested models in which consciousness arises from quantum computations within microtubules inside neurons, a controversial theory known as OR, orchestrated objective reduction, proposed by Sir Roger Penrose and Stuart Hameroff. If, and it's a huge if, such a model is correct, and consciousness can be maintained or reconstituted from quantum information, then perhaps what falls into a black hole is not lost forever. Instead, the pattern, the self, could be reconstructed elsewhere, perhaps by future civilizations, advanced AIs, or even natural processes in an emergent multiverse. In this sense, death inside a black hole would not be annihilation, but metamorphosis. And what of the black holes themselves? Are they uniform in their structure, or do they differ across space and time? Current astronomical observations suggest that there are several classes of black holes: stellar mass, intermediate mass, supermassive, and possibly even primordial black holes formed in the early universe. Each type would have vastly different gravitational properties. For instance, while a stellar mass black hole could spaghettify you long before you even reach the horizon, a supermassive one, like the one at the center of the Milky Way, would allow you to cross the event horizon without even noticing. What lies within that vast interior? Could there be a stable region, an interior space, of sorts, that is shielded from the singularity by some yet unknown quantum gravitational effect? Some speculative theories suggest the existence of a quantum core, where space-time geometry flattens out or becomes repulsive, creating a region of stability. Others propose that black holes contain entire universes, birthed in a bounce from a prior collapse. In this case, every black hole might be the seed of a new cosmos, a baby universe whose laws of physics are slightly different from ours, a kind of natural selection on a multiversal scale. This idea is formalized in the concept of cosmological natural selection, proposed by physicist Lee Smolin. In this model, universes that are better at producing black holes are more likely to spawn offspring, leading to a kind of Darwinian evolution among universes. If this model is true, then black holes are not endpoints, but reproductive organs in a grand cosmic life cycle. And survival within them could mean becoming part of the architecture of a new reality. Imagine it: you fall into a black hole, your atoms stretched, your mind shredded, your information encoded on a holographic screen. And then, perhaps in another domain of space-time, you are reconstituted. Not as you were, but as something new. Perhaps you exist in a universe with different physical laws, or as a being composed entirely of information, free of mass, traversing the ether of quantum space-time. Perhaps you become part of a civilization of survivors, conscious patterns who endured the plunge and emerged on the other side. In this vision, black holes are not prisons or incinerators. They are crucibles. They are where the old forms die, and new possibilities are born. They are engines of transformation and catalysts of evolution on a scale so vast we can scarcely imagine it. And while we have no empirical proof that such survival is possible, the fact that our best theories suggest it cannot be ruled out is a testament to the strangeness and grandeur of the cosmos we inhabit. We are still in the infancy of understanding black holes. Our theories are incomplete. Our instruments are limited. But what we do know is that black holes are not simple. They are complex, dynamic, and deeply entangled with the most fundamental questions we can ask about space, time, information, and existence. And so, we continue to speculate, not because we expect easy answers, but because the journey of asking those questions leads us closer to the truth, one mysterious gravitational singularity at a time. If we imagine the continuation of this extraordinary journey, both physical and theoretical, into a black hole, we must widen the aperture of our imagination to embrace realities that defy conventional understanding. For centuries, the universe has repeatedly taught us that our intuitions, evolved for survival on the savannas of Earth, are utterly inadequate for comprehending the deep, non-Euclidean geometry of the cosmos. The rules within a black hole, if we can even call them rules, in the way we understand them, might reflect a higher-order logic beyond classical physics. Here, the very notions of time, space, and cause and effect may be radically reordered. This is not just science, it is metaphysical inquiry in its purest, most consequential form. To consider survival in such an environment, one must first understand that black holes are not uniform entities. Their nature is dictated by three properties, according to the Noether theorem: mass, charge, and angular momentum. But within these constraints lies a world of variety. A Schwarzschild black hole, which has no charge or spin, is theoretically the simplest type and has a non-rotating, spherically symmetric structure. Yet these are purely mathematical ideals. Most black holes in the universe are likely Kerr black holes, rotating masses that twist spacetime itself into a helical structure. This rotation introduces a region known as the ergosphere, lying just outside the event horizon. In this area, the fabric of spacetime is dragged around the black hole at such a velocity that nothing can remain stationary. This frame-dragging effect may open up exotic possibilities. Theoretically, it allows for energy extraction via processes like the Penrose process, which proposes that objects entering the ergosphere can split in two, with one part falling into the black hole and the other escaping with more energy than it initially had. This isn't just a curious fact of physics. It suggests that a rotating black hole is not entirely a one-way trap, but an object from which energy, and perhaps even information, can be extracted under precise conditions. Now imagine harnessing this effect with unimaginable precision. An advanced civilization with mastery over gravitational manipulation could, in principle, use a rotating black hole as an energy source, a propulsion mechanism, or even a portal, if space-time itself can be sculpted at such scales. Could such a civilization engineer a way to stabilize the throat of a wormhole inside the Kerr black hole, preventing collapse and allowing traversal into another region of the universe? It's not just idle speculation. Mathematically, solutions exist for traversable wormholes in Einstein's field equations, provided one introduces exotic matter, a theoretical form of matter with negative energy density. While we've never observed such matter, quantum field theory allows for it in certain contexts, such as the Casimir effect. Thus, the conceptual framework is in place. If exotic matter could be generated and stabilized, it might hold open a tunnel through spacetime, transforming a black hole into a viable conduit. Survival through such a tunnel would no longer rely on resisting spaghettification or enduring unimaginable temperatures, but on converting the very nature of the journey, not through a physical corridor, but a quantum informational channel. You would not traverse the black hole as a body, but as a waveform, a configuration of probabilities encoded in the trembling of the quantum vacuum. In this sense, survival becomes an act of translation. Much like how a photograph is transformed into bytes and reassembled on a screen thousands of miles away, a consciousness or object might be encoded, transmitted through the entangled nodes of spacetime, and reconstructed elsewhere. This idea may sound like science fiction, yet it's rooted in quantum teleportation, a real and demonstrable effect in the laboratory. It doesn't allow matter to be transmitted faster than light, but it does allow quantum states to be perfectly copied and reconstituted elsewhere, provided entanglement and classical communication are used together. Now apply that to a black hole. Suppose the event horizon acts as a kind of quantum scanner, destroying the classical body but encoding its quantum information in the fluctuations at the boundary, as predicted by the holographic principle. If the right conditions existed, a receiving end, a quantum link, a mechanism for reassembly, this information could, in principle, be used to reconstruct the traveler. The original would be gone, but the copy might live on. This raises profound philosophical questions. Is the copy you? If your memories, personality, and perceptions are preserved, but the original body is lost, have you survived? Or have you died, replaced by a doppelganger? These aren't just metaphysical ponderings. They are vital components of the survival equation. For if survival through a black hole is possible, it may not resemble survival as we understand it. Instead of walking away intact, you may emerge reborn, encoded in photons, stabilized in qubits, distributed through the ripples of space-time. The laws of physics do not forbid this. Rather, they point toward a reality in which identity is fluid, death is not final, and the self is a symphony played upon the strings of the universe. And yet, even if such survival were possible, it would require technology far beyond our comprehension. We would need the power to manipulate Planck-scale physics, to control the curvature of space, to tame the chaos of the singularity. We would need to decode the language of the universe at its most primal level, a level where time ceases to be a line and becomes a loop, where matter becomes energy, and where energy becomes thought. But perhaps that is our destiny. For all of human history, we have pushed against the edges of our limitations. We once believed the Earth was the center of the cosmos, that the stars were fixed, that time was absolute. Each time, we were wrong. Each time, the truth was grander and more mysterious than we dared to imagine. Why should black holes be any different? They may be the ultimate crucibles, testing not just our technology but our philosophies, our faiths, and our dreams. They challenge us to ask what it means to be alive, to be conscious, to exist. And they hint that the answers may lie not in resisting death, but in embracing transformation, into something unrecognizable, something post-human, something eternal. But even as we let our imagination scale the steep walls of possibility, we must return, again and again, to the indomitable forces that define a black hole's true nature. Tidal forces remain one of the most prominent barriers to any hope of survival. As you approach the singularity, the gravitational pull across your body becomes so unequal that your feet could be tugged with an incomprehensibly stronger force than your head. This phenomenon, aptly nicknamed spaghettification, is not mere exaggeration, it is a real consequence of the warped geometry of space near a point of infinite density. To put it plainly, the gravitational gradient becomes so steep near a singularity that anything falling in is torn lengthwise into a long, thin filament of atoms. It's not just a crushing experience, it's a shredding of the atomic structure, molecule by molecule, until all that remains is a smear of particles stretched along the line of fall. This effect becomes more dramatic with smaller black holes, because the event horizon lies closer to the singularity. For a stellar mass black hole, you'd be spaghettified long before crossing the horizon. But for a supermassive black hole, millions or even billions of times more massive than our Sun, the tidal forces at the horizon are gentler. In that case, you could theoretically cross the event horizon without immediate physical destruction. You wouldn't feel anything unusual at first. You wouldn't even see the horizon as a visible line. You'd drift past it in silence, suspended in a sea of distorted starlight. But even if you escaped spaghettification at the border, the singularity would still await. And as you continued falling, time itself would begin to behave strangely. According to general relativity, from the perspective of a distant observer, your fall would slow down, taking an infinite amount of time to reach the event horizon. Light from you would become redshifted, fainter, and eventually invisible. But from your own frame of reference, time ticks on normally. You continue falling. Seconds pass, then minutes, then maybe hours, and the surrounding universe fades as you approach the inescapable heart of the black hole. At this point, physics begins to break down. Not metaphorically, but literally. The Einstein field equations that have so accurately described the warping of spacetime begin to generate infinities, quantities with no physical meaning. Density becomes infinite. curvature becomes infinite. This is what we call a singularity. Not because it is a point in space, but because our mathematics can no longer describe it. It is the ultimate boundary of knowledge, a veil drawn across the face of reality. What happens here? Does the singularity destroy all information? Or does it store it in some arcane, encoded form? This is the heart of the black hole information paradox, a problem that has haunted physicists for decades. Stephen Hawking once suggested that information is irrevocably lost inside black holes, a proposal that flies in the face of quantum mechanics, which insists that information must be preserved in any physical process. This tension between quantum theory and general relativity has fueled one of the deepest and most important debates in modern physics. But recent theoretical work offers a glimmer of resolution. One promising framework is the holographic principle, which suggests that all the information swallowed by a black hole is actually stored on its surface, the event horizon, like a cosmic hard drive. This isn't just science fiction. Calculations from string theory and quantum gravity imply that the universe itself may be holographic, a three-dimensional illusion projected from a two-dimensional boundary. If true, this could mean that the interior of a black hole, the part that seems to destroy information, may be a kind of holographic projection, with the real data encoded on the horizon. In that case, the story of survival changes again. You may fall in and be destroyed, at least in your classical form, but the information that constitutes your being might remain smeared across the black hole's surface. Could it be retrieved? Could it be decoded? Could it even be restored in another region of space, like a puzzle reassembled from scattered pieces? This is where quantum mechanics may offer hope. Theoretical models now suggest that black holes emit subtle radiation, what Hawking called Hawking radiation, which slowly leaks information back into space over trillions of years. At first, it seemed this radiation was purely random. But newer work argues that it may, in fact, carry encrypted data about the interior of the black hole. If this is true, it implies that information is not lost, but transformed, and that, with enough time and the right tools, it could be reconstructed. Let us be clear, the time frames involved here are cosmic. The evaporation of a supermassive black hole via Hawking radiation could take a quadrillion years or more. For comparison, the universe itself is only about 13.8 billion years old. So this process is not something that could be observed or exploited by any current, or even near-future civilization. But it is possible. And in physics, possibility is everything. Some have taken this even further. The idea of black holes as white holes, in reverse, a concept born from mathematical symmetry, suggests that the matter and energy absorbed by a black hole could one day be expelled in a burst of radiant release. This notion is still speculative, but it leads to fascinating implications. Could our universe itself be the interior of a black hole formed in a parent universe? Could a black hole serve not as an end, but as a beginning? If so, a journey through a black hole might not be a journey toward death, but toward creation, toward the birth of new space, new time, and perhaps even new life. This doesn't mean you or your spaceship would survive the trip, but the information encoded in your atoms, your thoughts, your being, might seed a new cosmos. You could become the building blocks of another reality, in a very literal sense. Of course, this brings us back to philosophy. What does it mean to survive? Is it the continuity of your memories? Your consciousness? Your atomic structure? Or is it enough that some trace of you remains, that you influence what comes next, even if you do not witness it? A journey through a black hole is not simply a test of engineering or biology. It is a test of identity, of what it means to endure, of whether we are defined by our form, or by our function, by our particles, or our patterns. And as strange as all of this sounds, the universe itself seems to be nudging us toward such questions. Every advancement in physics, from relativity to quantum theory to holography, points to a cosmos far more flexible, far more layered, than we ever imagined. A cosmos where death and survival may be two sides of the same Mobius strip. In contemplating whether we could survive a journey through a black hole, we must venture far beyond the realm of conventional science. It's no longer enough to think in terms of rockets and metal hulls. We must delve into the architecture of space-time itself, into speculative physics, and even into the limits of human consciousness and information theory. Because survival in this context is no longer a matter of biology, it is a matter of physics, of metaphysics, and ultimately, of cosmology. At the heart of the black hole lies a paradox. On the one hand, general relativity tells us that the singularity is an endpoint, a place where density and gravity become infinite, where the equations break down and predict nothing but doom. On the other hand, quantum mechanics, which governs the tiniest particles of the universe, refuses to accept this fate. In the quantum realm, information cannot be destroyed. Every electron, every photon, every pattern of entangled particles must, somehow, be preserved. So when something falls into a black hole, whether it's a star, a planet, a human being, or even a simple particle, the question becomes, where does its information go? To answer this, let's revisit the concept of Hawking radiation. According to Stephen Hawking, black holes are not entirely black. Due to quantum fluctuations at the event horizon, pairs of particles can spontaneously appear, one falling in, the other escaping into space. Over eons, these escaped particles allow the black hole to gradually evaporate. At first glance, this seems to suggest that black holes eventually disappear completely. But if they vanish, what happens to all the information they once contained? If it's gone forever, that violates quantum mechanics. If it escapes, then it must be hidden somewhere in the radiation. This led to one of the most significant debates in modern physics, the black hole information paradox. Hawking argued that the information was truly lost, causing a firestorm in the scientific community. For decades, physicists tried to reconcile this with quantum theory. Then, proposals emerged suggesting that the event horizon itself might encode the information. This gave birth to the idea of the holographic principle, which posits that the three-dimensional world inside a black hole, including everything that has ever fallen into it, could be described entirely by information on its two-dimensional surface. Imagine for a moment that this is true. Imagine that the black hole's surface is like a cosmic record, etching every photon, atom, and strand of DNA that crosses its boundary into a vast, unfathomable storage system. You fall in, and from your point of view, you are plunging deeper and deeper into darkness. But from the outside, your information is frozen at the horizon, distorted, encrypted perhaps, but not gone. Over time, as the black hole radiates away its mass, the information slowly leaks out in the radiation. Theoretically, if we had a perfect understanding of quantum gravity and a vast enough computer, we could decode that radiation and reconstruct everything the black hole had swallowed, including you. This stretches the definition of survival. You, as a conscious being, would be shredded, torn into subatomic confetti. But the information that made you who you are, your genetic code, the synaptic patterns in your brain, the structure of your memories, would still exist, albeit in a transformed state. Does this count as survival? Is a copy of you, made from the original data, still you? Let's go deeper. Suppose you could somehow shield yourself from spaghettification. Perhaps you're falling into a supermassive black hole, where the gravitational gradient at the event horizon is gentle enough not to rip you apart instantly. Suppose you are inside a spacecraft designed to resist even immense pressures, equipped with speculative materials like metallic hydrogen or graphene reinforced with exotic matter. You cross the horizon. From the outside, time appears to stop. But for you, time proceeds as normal. Your sensors detect nothing unusual. There is no flash of light, no sudden tug, just a slow dimming of the universe behind you. Inside the event horizon, all paths lead inward. Space and time switch roles. Moving forward in time becomes synonymous with falling toward the singularity. You cannot hover, cannot turn around, cannot escape. Even if you fired engines with the strength of 1,000 suns, they would only hasten your fall. You are inside the gravity well's ultimate boundary. And the singularity is now not just a place you will fall toward, but a moment in your future, an inevitable point in your timeline. But the nature of this singularity is unknown. Some physicists believe that quantum gravity, whatever final theory unifies Einstein's general relativity with quantum mechanics, may smear out the singularity. Instead of a point of infinite density, there may be a Planck-sized region where space and time loop in on themselves, or where new dimensions open up. In such models, the singularity is not a destructive endpoint, but a gateway, a bridge to another region of spacetime. This is the basis of the black hole-wormhole connection. Wormholes, or Einstein-Rosen bridges, are solutions to the equations of general relativity that connect two different regions of spacetime. In theory, a black hole could be the entrance to such a tunnel, and a white hole, the time-reversed counterpart of a black hole, could be the exit. You fall into a black hole in one part of the universe, and emerge from a white hole in another, possibly in a different galaxy, or even in a different universe. This is the ultimate science fiction fantasy, using black holes as portals for faster-than-light travel. But wormholes come with severe caveats. They are unstable, prone to collapse unless held open by negative energy, something we have not yet observed in sufficient quantities. Exotic matter with negative energy density, required to stabilize a traversable wormhole, may exist in principle, but no known material exhibits this property. Furthermore, even if a wormhole could exist, the immense radiation and tidal forces near a black hole might destroy anything trying to enter it. Still, the idea remains tantalizing. Could an advanced civilization, millions of years beyond us, harness the power of quantum gravity, tame the singularity, and transform black holes into bridges? If so, they might seed artificial black holes with information, store data for eons, or travel across galaxies in moments. They might dwell near the event horizon, conducting research on the deepest mysteries of the universe. And this raises the ultimate question: what if we've already encountered such intelligence? Some have speculated that black holes themselves could be signs of advanced life, machines built to store or process information on an astronomical scale. Perhaps an alien species, faced with the end of their star or their galaxy, decided to upload their entire civilization into the quantum state of a black hole. A cosmic server, housing the souls of 1,000 worlds. We don't know. We may never know. But in asking whether we could survive a journey through a black hole, we are really asking something deeper. Not just whether our bodies can endure the pull, or our ships resist the crush, but whether our consciousness, our stories, our thoughts, our essence, can persist beyond the veil. And in that pursuit, the black hole is not a prison. It is a mirror. It reflects back the limits of our understanding, the boundaries of our courage, the nature of our soul. It challenges us not just to survive, but to transcend. To imagine what it would mean to transcend within the confines of a black hole is to press our understanding of life, existence, and consciousness into uncharted territories. It's one thing to talk about surviving physically, and quite another to explore what it would mean to persist informationally, cognitively, or perhaps in some quantum-encoded, non-corporeal sense. And yet, given the extremity of black holes, this is where the conversation inevitably leads us, into a domain where survival is no longer about breath or heartbeat, but about the raw continuity of being, in any conceivable form. Let us reframe the concept of survival in the context of what black holes challenge: the very flow of time, the integrity of space, and the assumption that information travels in predictable paths. Once you fall into a black hole, you are not merely being consumed, you are being redefined. Time, within the event horizon, behaves like space, and space behaves like time. Your future is now inevitably aimed at the singularity. The idea of turning back, of retracing your steps, is a fantasy. Yet despite this, your experience, your subjective sense of reality, will not end abruptly. Depending on the size of the black hole, you might not feel any drastic changes right away. In fact, in a supermassive black hole, you could fall in without any initial harm at all. The ride could be eerily smooth. Your instruments would eventually become unresponsive, the universe behind you would appear frozen in time, and ahead, there would be nothing but inescapable collapse. But the clock would still tick. Thought would still occur. Neurons, or whatever quantum equivalents might exist in more speculative constructs of mind, would still fire. In those final moments, or minutes, or even hours depending on the nature of the black hole, you would have time to think, to contemplate the nature of your journey, to consider the irreversible plunge you've undertaken. Would it be horrifying, enlightening, or perhaps strangely peaceful? In that sense, your final descent into the singularity, a journey into the unknown, where all boundaries between the observer and the observed begin to blur. But suppose something even more incredible. What if the singularity isn't a dead end at all, but a transformation point? According to some versions of loop quantum gravity, a candidate for a theory of quantum gravity, the singularity doesn't exist in the traditional sense. Instead, the extreme gravitational compression could cause a bounce. Rather than matter and energy being crushed into nothingness, they could be reconfigured and ejected into a new expanding region of space, essentially, the birth of a new universe. This idea isn't just abstract speculation. It emerges from serious attempts to reconcile quantum mechanics with general relativity. In this model, black holes become seeds of creation, the wombs of new realities. If you could somehow survive to the bounce, you might emerge, transformed, unrecognizable perhaps, but continued in some way. This is where survival becomes a truly philosophical question. What does it mean to be you? Is it your physical structure, your pattern of thought, your memories, or something even more ephemeral, like continuity of perception? If your data is preserved through the black hole and reassembled in another universe, are you still you? This scenario pushes us to consider continuity of identity beyond physical preservation. Even if your consciousness couldn't be carried through, could a perfect replica, built from the information encoded in the black hole's structure, be an extension of you? This brings us to the concept of black hole complementarity, a theory that attempts to resolve the paradox of information loss. According to this idea, there is no single, consistent description of what happens to an object that falls into a black hole. For an outside observer, the object never quite crosses the event horizon. It appears frozen in time, smeared across the surface, and eventually radiates back out through Hawking radiation. But for the falling observer, they cross the horizon without noticing anything unusual and continue toward the singularity. Both descriptions are true in their own frames of reference, yet they cannot be reconciled. This duality suggests that reality itself is observer-dependent. The universe may not be a fixed, objective entity, but rather a mosaic of overlapping perspectives, each with its own truth. In such a universe, survival might be equally relative. From your perspective, you died in the singularity. From another, you became a part of the cosmic memory embedded in the black hole's surface. From yet another, you were encoded into the fabric of a new universe, born of the gravitational collapse that ended your journey. Perhaps all of these things happened. Perhaps none of them did. If this all sounds like metaphysics, it's because we are now treading on the border where physics becomes indistinguishable from philosophy. And yet, it is a frontier grounded in real science. Black holes are not mere theories. They are observed phenomena. We see stars orbiting invisible giants at the centers of galaxies. We detect gravitational waves from black hole mergers. We have even imaged the shadow of a black hole, surrounded by glowing plasma. These are not speculative entities. They are real, and they are shaping our understanding of the universe. As we continue to explore their nature, through telescopes, simulations, and equations, we are not merely trying to map a distant, exotic region of space. We are trying to understand the deepest workings of reality. We are trying to understand what happens to time, to space, to information, and to ourselves, under the most extreme conditions imaginable. Black holes are nature's test chambers, where the laws of the cosmos are bent to their limits. And in entering them, even in thought, we confront the most profound question we can ask: can the essence of who we are transcend the bounds of space-time? As this journey continues, we will explore not only what black holes are, but what they could become: gateways to new realities, cosmic computers, engines of creation, and perhaps even the crucibles of immortality. The deeper we dive, the more we see that this is not a question of mere physics. It is a question of being. And it has only just begun. So, let us now go deeper, not just into the heart of the black hole, but into the heart of the theories, assumptions, and daring speculations that try to unravel this cosmic mystery. If the singularity at the core of a black hole is truly a place where all known laws of physics collapse, then by definition, our models must break there. But science is not content with saying, "This is where understanding ends." Instead, this point of infinite density and zero volume becomes a challenge, an invitation to build new physics capable of piercing the veil of the singularity. Quantum gravity, the elusive holy grail of theoretical physics, holds the key. It promises a unification of the smooth, geometric world of general relativity and the probabilistic, discrete realm of quantum mechanics. If successful, it could allow us to predict what happens beyond the event horizon and even inside the singularity, not with hand-waving metaphors or guesswork, but with actual, testable mathematics. One of the front-running candidates in the quest for quantum gravity is string theory, a framework in which all particles are actually tiny vibrating strings of energy. In string theory, black holes can be described not as infinitely dense points but as extended, higher-dimensional objects called brains. These brains may hold the secret to understanding how information is preserved, how spacetimes evolve, and whether other universes can emerge from black hole cores. Some versions of string theory suggest that the singularity isn't a point of infinite density at all, but rather a gateway or portal, a region where higher dimensional effects dominate and allow for strange phenomena such as dimensional transitions or even brain collisions that might birth entire universes. Another candidate theory, loop quantum gravity, attempts a different approach. Rather than viewing space as smooth and continuous, loop quantum gravity treats it as granular, a fine lattice of loops that define how space is quantized. Inside this model, the singularity may not exist in the classical sense. Instead, as the matter within the black hole collapses, it reaches a minimum volume before bouncing back, initiating a new expansion phase. This theoretical Big Bounce scenario raises profound questions. Could our own universe be the result of such a bounce from a black hole in another cosmos? If so, then every black hole in our universe could potentially be a seed for a new universe in a vast and endlessly branching multiverse. If these theories hold any truth, then survival through a black hole might mean more than holding your body together. It might mean being reborn as part of a new cosmos. The data that makes up your body and mind might be disassembled and restructured, reseeded into the physics of a new realm. You would not emerge on the other side in the same form, but in a different expression of the same information. This, again, presses us to ask, is that survival, or is it merely transformation? Let's now revisit one of the most tantalizing ideas, that black holes might function like cosmic computers. The physicist Seth Lloyd proposed that the entire universe can be seen as a quantum computer, processing information at a fundamental level. Within this perspective, black holes could represent the most powerful computers of all, compressing and encoding vast quantities of data in incredibly small volumes. The surface of a black hole, its event horizon, acts like a screen, storing information about everything that has fallen in. This concept is grounded in the holographic principle, which posits that all the information contained within a volume of space can be represented by data encoded on its boundary. That means the three-dimensional world we experience might, at the deepest level, be a projection from a two-dimensional surface, a kind of cosmic hologram. If black holes obey the holographic principle, then everything that crosses the event horizon is not lost, but rather its data is smeared across that two-dimensional surface. Over time, that data is radiated back out into the universe as Hawking radiation, a form of entropy, perhaps, but not pure destruction. In this view, falling into a black hole might not be annihilation, but transcription. Your body, mind, memories, all of it, is encoded, preserved in a form so alien and compressed that we struggle to imagine it. But it's there, humming on the quantum horizon, waiting to be decoded. Let us take a moment to imagine what this encoding might mean on a cosmic scale. Picture civilizations, entire alien empires, now long gone, that once ventured into black holes not in desperation, but in hope. They might have seen these dark stars not as death, but as escape, as ascension. Perhaps they developed technologies so advanced that they could preserve themselves not as matter but as pure information, uploaded into the black hole's horizon, a digital memory etched into the cosmic code. Their civilizations might now exist in a form of slow-motion eternity, living on the edge of time itself, each millisecond stretched out over what would seem to us like billions of years. Could this be the future of intelligence in the universe? Not in sprawling megastructures, but as whispering shadows on the edge of black holes, the last embers of thought flickering across the quantum screen of spacetime. And yet, even if this vision is true, we must contend with the enormous technological and philosophical challenges it presents. How could we ever retrieve this information? How would we translate it back into something meaningful, into something human? Even if the data that made up a person were preserved, the arrangement, the context, the spark of consciousness might be gone. What returns might be a static snapshot, a fossil, not a living mind. Still, for a species desperate to cheat death or escape the heat death of the universe, black holes might become the ultimate refuge. They may represent the final libraries of the cosmos, preserving the knowledge, memory, and essence of everything that ever lived. Even today, scientists are probing these ideas with more than philosophical curiosity. Experiments in quantum information theory, black hole thermodynamics, and holography are testing these concepts on the edge of theoretical physics. Researchers are exploring whether quantum entanglement, the mysterious phenomenon where particles separated by vast distances still affect one another, might hold the key to how information escapes a black hole. This is not mere science fiction, it is the cutting edge of our attempt to reconcile quantum mechanics with gravity, to unlock the secrets that lie at the foundation of reality. And so, the deeper we go, the more the black hole begins to resemble not just an object, but a mirror. A mirror that reflects our ignorance, our dreams, our fears, and our aspirations. It shows us how little we truly know about the universe, about time, and about ourselves. But it also beckons us forward. For within the darkness of the black hole lies a promise, that if we are brave enough to ask the right questions, we may yet discover answers more profound than anything we've ever known. This promise of understanding black holes isn't just rooted in the esoteric beauty of theoretical physics. It also touches the practical potential of future technologies and human advancement. Let's speculate even more boldly. What if, someday, humanity constructs spacecraft not merely capable of approaching a black hole, but of utilizing it? The notion may seem absurd today, but every great leap in science began with absurdity. Wormholes, if real and traversable, might provide shortcuts through spacetime, enabling us to reach other galaxies in minutes. A highly advanced civilization might build artificial black holes to create these wormholes deliberately, mastering control over singularities to bend space and time to their will. Such feats would demand unimaginable energy and precision, yet they're not forbidden by known physics. They're just far beyond our current capabilities. To even consider such applications, we must understand the delicate interplay between a black hole's mass, spin, and charge. Theoretically, a rotating black hole, described by the Kerr solution to Einstein's field equations, possesses an inner region called the ergosphere. Here, spacetime itself is dragged around the black hole in what's called frame dragging. This effect creates a zone where energy and momentum can, in theory, be extracted. This process, first proposed by Roger Penrose, suggests that if you threw an object into the ergosphere and split it in two, one part could fall into the black hole while the other escapes with more energy than the original object had. This Penrose process may be more than a clever thought experiment. It may hint at energy generation methods that a super-advanced civilization could exploit. Instead of avoiding black holes, such civilizations might orbit them like power plants, siphoning off rotational energy to power their machines or interstellar infrastructure. This leads us to the incredible idea of black hole farming. Imagine building colossal arrays of satellites or Dyson sphere-like structures around a rotating black hole, capturing the energy radiated from its accretion disk or from the Penrose process. These structures could feed on the black hole's rotational energy for millions of years. Not only would such engineering be among the greatest feats of intelligent life, but it might also be detectable across the cosmos. In fact, some astronomers have proposed scanning the skies for anomalies in infrared radiation, signatures that might indicate advanced civilizations already utilizing black holes in this way. The possibilities don't end there. Let's revisit the idea of time dilation, which we touched on earlier. Near a black hole's event horizon, time slows down significantly due to the intense gravity. This isn't just a theoretical curiosity, it has profound implications. For astronauts orbiting close to the event horizon, days might pass for them while centuries flow by for the rest of the universe. This time shelter could, in theory, serve as a way for a civilization to escape existential threats. Suppose a species foresees a catastrophic event, like a gamma-ray burst, galactic collision, or even heat death. If they can station themselves close to a black hole's event horizon, they might wait out the danger while experiencing only a fraction of the time. When they emerge, the universe would be older, but perhaps more hospitable, or ready for rebirth. Of course, we must return to the harsh reality of spaghettification. The gravity gradient near the singularity is so steep that, as you fall in feet first, your legs would feel a much stronger pull than your head, stretching you into a long, thin strand of atoms. This tidal force increases exponentially as you approach the singularity. But here's an interesting twist. For supermassive black holes, such as the ones at the centers of galaxies, this gradient is more gradual. The event horizon is so vast, sometimes as wide as the orbit of Earth, that you might pass through it without even realizing it. The gravitational pull, while strong, would be uniform across your body. This means that, at least temporarily, you might survive entry into a supermassive black hole without being immediately torn apart. This opens a fascinating line of speculation. If we were ever to attempt a journey through a black hole, we would target a supermassive one. We need to avoid the searing heat and radiation of the accretion disk, dodge the lethal gravitational shear of stellar mass black holes, and plunge gently through the event horizon of one that's millions of times more massive than the Sun inside. Time and space would swap roles. You wouldn't be able to escape back the way you came, because every possible direction would lead inward, toward the singularity. Yet you wouldn't necessarily feel anything different, at least not at first. You'd be carried forward by the flow of space-time itself, deeper and deeper, until eventually, your fate would depend entirely on the true nature of singularities. Here's where science truly enters the unknown. In general relativity, singularities are points of infinite curvature and density, a breakdown of the laws of physics. But quantum theory abhors infinities. It insists that something else must happen, some new state of matter, or some new geometry of spacetime, must emerge to replace the singularity. Some theorists speculate that the core of a black hole could transition into a wormhole throat, linking to another region of spacetime. Others suggest that the singularity is replaced by a Planck star, a hypothetical object in loop quantum gravity where matter rebounds due to quantum pressure. This rebound might look, from the outside, like a black hole slowly evaporating via Hawking radiation. But from the inside it could resemble a white hole, a time-reverse black hole that spews matter and energy instead of swallowing it. If white holes exist, and if they are connected to black holes, then every black hole might be a portal, not to death, but to Genesis. A spacecraft falling into a black hole might, after enduring unimaginable stresses and compression, emerge into a new region of spacetime. The problem, of course, is that the one-way nature of the event horizon makes this unverifiable. Any information sent back from inside would be lost to the outside world. But maybe, just maybe, the structure of the universe itself bears traces of this process. Some physicists argue that the birth of our universe, the Big Bang, might actually have been the result of matter bouncing from a black hole singularity in another cosmos. In this cosmological model, each black hole births a new universe with slightly different physical constants, evolving and growing in its own distinct timeline. If that's true, then perhaps consciousness and life are not accidents in a sterile cosmos, but fundamental elements in a universe designed to propagate complexity. Each universe gives rise to black holes. Each black hole spawns a universe, and in those universes, intelligence may arise to understand and participate in the grand cycle of cosmic creation. We would be, Not just spectators in a universe governed by blind laws, but agents in a self-replicating cosmic loop, explorers, creators, and maybe even eventual engineers of new universes. And so, our journey through a black hole ends where it began, in mystery. Could we survive it? Not in the biological sense we know today, but perhaps in a more abstract form, as information, as energy, as part of a larger story that stretches beyond the visible stars. Black holes may not be death, they may be doors. They may be firewalls, or they may be archives. They may be the greatest threat, or the ultimate opportunity. What's clear is that they are not to be feared in ignorance, but approached with wonder. They represent the deepest truths about space, time, matter, and the limits of human understanding. And the more we look into them, the more they reflect us, not as we are, but as we might become. Our imagination may carry us far, but so too must our understanding. To truly envision surviving a journey through a black hole, we must now dive deeper, not just into the physical characteristics of black holes, but into the conceptual frameworks that might allow us to model, navigate, and even manipulate them. For instance, the singularity, often treated as a mere point of infinite density, may in fact be better understood through quantum gravity, a yet-to-be fully realized theory that attempts to reconcile general relativity with quantum mechanics. The two dominant candidates for such a theory, string theory and loop quantum gravity, offer competing but deeply compelling visions of what lies at the core of a black hole. String theory posits that the fundamental constituents of the universe are not point-like particles, but vibrating strings of energy. According to this framework, under extreme conditions like those inside a black hole, strings could stretch, loop, and interact in ways that completely alter our classical expectations. Rather than a singularity, a tangled, oscillating string network may form a compact, complex object, a stringy core that avoids the infinities predicted by general relativity. If this is true, then a traveler falling into a black hole might encounter a realm of exotic string interactions, where space and time themselves shimmer with quantum uncertainty. Movement through such a space could resemble nothing we can presently visualize. It would require a new language, a new physics, perhaps even a new logic to describe. Meanwhile, loop quantum gravity approaches the problem from a different angle. It suggests that space itself is not continuous but made up of discrete loops of quantum information. Imagine a vast network of interconnected rings, each one representing a fundamental unit of volume. Near a black hole's core, this looped fabric could become so tightly compressed that it resists further collapse, producing a bounce instead of a singularity. This rebound could potentially give birth to a white hole, where the matter and energy previously swallowed are expelled in a controlled, perhaps even predictable, fashion. The implications of this are profound. If the black hole's core is not a death trap but a quantum rebirth engine, then maybe survival isn't about resisting destruction, but about being transformed, carried along on a quantum current into a new region of spacetime. But let's push beyond the theoretical. Could technology, eventually, be developed to harness these ideas? Imagine a spacecraft equipped not only with shielding capable of resisting radiation and gravitational stress, but also with onboard artificial intelligence systems capable of real-time space-time computation. These systems wouldn't just calculate trajectories in normal space. They would model quantum space-time probabilities, determining the safest pathway through gravitational singularities. Such a craft might use the black hole's own properties, its rotation, charge, and geometry, as navigational tools. It could align with the black hole's axis of rotation to avoid frame-dragging chaos, dive in with precision timing to exploit stable space-time corridors, and even utilize quantum entanglement to maintain communication with the outside world, or at least, with another segment of the same multiversal structure. Of course, this borders on the speculative, even the fantastical. But then again, so did the idea of black holes themselves for many decades. When John Michell first proposed the idea of dark stars, in the 18th century, they were nothing more than mathematical curiosities. When Einstein's equations implied the possibility of singularities, even he resisted the idea. It took generations of theoretical and observational work before black holes were accepted as physical entities. So who is to say that the idea of traversing them, or surviving them, is out of bounds for the next wave of human exploration? Let us also consider the importance of observation and indirect measurement. Since we can never retrieve signals from inside the event horizon, we must rely on what happens just outside it. And here, we encounter a vital clue: the black hole's information paradox. According to quantum mechanics, information can never be truly destroyed. But classical descriptions of black holes suggest that all information that crosses the event horizon is lost forever. This contradiction has spurred decades of debate among physicists. Stephen Hawking, initially convinced that information was lost, later conceded that it might be encoded in the Hawking radiation that slowly leaks from the black hole's surface. This revelation transforms black holes from dead ends into cryptic messengers. If we could decipher the patterns in Hawking radiation, we might unlock the secrets of whatever lies within, including, possibly, the fate of anything that enters. There's also the strange and haunting possibility that reality itself is a hologram. The holographic principle, derived from string theory and bolstered by studies of black hole thermodynamics, suggests that all the information within a volume of space can be encoded on its boundary surface. Applied to black holes, this means that everything that falls in might be preserved, somehow, on the two-dimensional event horizon, just like a holographic plate stores three-dimensional images. If true, this idea radically reshapes our understanding of what it means to survive a journey through a black hole. Perhaps survival doesn't mean continuing in our original form. Perhaps it means being preserved, recorded, translated into patterns of quantum information on the event horizon itself. Perhaps those patterns can be reassembled, reinterpreted, or even reborn in another region of space and time. We are, in many ways, only at the dawn of understanding. With the Event Horizon Telescope, we've taken the first image of a black hole's shadow, M87*, a supermassive behemoth in a distant galaxy. We've measured the gravitational waves produced when black holes collide, ripples in spacetime that whisper of hidden cataclysms. We've built models of stellar evolution that explain how massive stars die and collapse into these cosmic sinkholes. But the journey is just beginning. With each new discovery, we refine our tools, expand our imaginations, and approach the ultimate questions with ever greater clarity. And in that light, maybe the question of surviving a journey through a black hole is not just about physics. Maybe it's a question about ourselves. About our courage to face the unknown. About our willingness to imagine new futures, new realities, and new forms of existence. Because to contemplate the black hole is to contemplate the edge of reality itself. And if we have the strength to peer over that edge, into the dark, into the unknowable, then perhaps, just perhaps, we'll find that survival isn't about resisting gravity, but about embracing transformation. About evolving with the cosmos, adapting to its wildest extremes, and becoming part of the infinite story that black holes may yet reveal. If we are to continue speculating on the possibilities of surviving a journey through a black hole, we must now consider what role consciousness might play in such an environment. This may sound abstract, even philosophical, but it touches upon one of the most profound questions of modern science. Is consciousness an emergent byproduct of brain activity, or is it a fundamental property of the universe, as some interpretations of quantum mechanics and panpsychism propose? If the latter holds any truth, then our very perception of time, space, and identity may be fundamentally altered during extreme gravitational experiences, perhaps giving rise to forms of awareness or experience we have yet to conceptualize. Imagine falling into a black hole, and rather than being torn apart instantly by tidal forces, your consciousness undergoes a kind of phase shift. Time slows down infinitely as you approach the event horizon, but from your perspective, time continues normally. This leads to one of the most paradoxical features of black holes. From the outside, you appear frozen in time at the edge, slowly redshifting into invisibility, while internally, you pass through the event horizon in what seems like finite time. What does this imply about your subjective experience? Could a mind, in such conditions, be sustained in a temporally dilated state indefinitely, preserved like a fly in amber within the space-time curvature? This concept also intersects with proposals like black hole complementarity, a theoretical principle suggesting that no observer can witness the duplication or destruction of information. For an outside observer, all your information is smeared on the horizon. For you, the infalling observer, you experience falling into the black hole as normal, at least until the inner physics become extreme. These two narratives are mutually exclusive, and yet simultaneously valid, depending on the observer. It's a principle reminiscent of the many worlds interpretation of quantum mechanics, where each decision or event branches into its own universe. So could it be that each passage through a black hole spawns new realities, not just physically, but experientially? Now consider the implications of hypothetical constructs like traversable wormholes, essentially black holes that link 2 points in space-time via a tunnel-like geometry. For a wormhole to be traversable, it must be stable, and to be stable, it must resist collapse. Classical physics doesn't permit this without exotic matter, material with negative energy density that can hold the throat of the wormhole open against the immense gravitational pressures. The Casimir effect, a quantum mechanical phenomenon observed in very small scales between parallel plates in a vacuum, demonstrates that negative energy does exist. But we have yet to engineer this at a scale capable of stabilizing a cosmic shortcut. Still, imagine we could. Imagine a civilization, perhaps millions of years ahead of us, capable of generating and manipulating negative energy. They could potentially construct a wormhole entrance, disguised as a black hole from the outside, and another entrance far across the universe. Theoretically, they could use it to travel, send information, or even evacuate themselves from a dying galaxy. For such a species, black holes would not be the ends of time and space. They would be bridges, passages, even gateways to engineered realities. If we one day crack the code of negative energy and quantum space-time geometry, we too might harness such power. And what of white holes, the theoretical opposites of black holes? Where black holes suck in everything, white holes expel matter and energy, allowing nothing to enter. While we've never observed one directly, they arise naturally in the mathematical time reversal of black holes. Some theorists even propose that the Big Bang itself may have been the result of a white hole explosion, the end of one universe's black hole collapse triggering the beginning of our own. If true, this opens the door to a breathtaking vision, black holes as seeds of creation, where each collapsing star births not an end, but a beginning, in some other dimension or timeline. Survival, in this scenario, becomes not a matter of resisting collapse, but of passing through it into genesis. But let's return to the concept of spaghettification, the dramatic stretching and compression that matter experiences near a black hole due to differential gravitational forces. Could anything, even theoretically, survive this? In the case of supermassive black holes, the tidal forces at the event horizon are surprisingly gentle because the gradient is shallow over larger distances. This means you could theoretically cross the event horizon without feeling anything unusual, at least initially. It's only when you near the singularity that the forces grow intolerable. This gives us a narrow window of opportunity. If we could develop propulsion systems, shielding, or even structural mechanisms that respond dynamically to gravitational gradients, we might delay or even survive those interior stresses long enough to navigate or exit through a quantum channel. We must also consider the role of dark matter and dark energy, mysterious substances that make up the majority of the universe's mass-energy content. We know black holes interact with dark matter, possibly forming dense spikes of it around them. Could there be hidden dynamics here that we've yet to decode? Could dark matter streams influence the internal geometry of black holes, or even offer protective pathways through them? What if dark matter, immune to electromagnetic interaction, is not torn apart by tidal forces in the same way baryonic matter is? Could embedding ourselves in a dark matter shell provide shielding? It's speculative, yes, but so is all great exploration at its frontier. There's also the possibility of black holes acting as computational engines. Seth Lloyd, a quantum information theorist, proposed that black holes are the ultimate computers, processing information at the limits of physical law. Every interaction at the event horizon, every infall of mass and energy, may be encoded, compressed, and transformed within a cosmic processor of unfathomable density. If we could understand the language of such computation, we might learn how to input and retrieve data, effectively turning black holes into cosmic servers. In that case, survival could mean uploading oneself into the quantum foam at the event horizon, to be reconstituted or transmitted elsewhere. Not survival of the body, but of the mind, of the pattern, of identity itself. Let us not forget the deeper philosophical implications. Black holes may represent not just physical limits, but epistemological ones, the boundary beyond which our current models fail. They force us to reckon with paradoxes, to unify general relativity with quantum theory, to confront the limits of determinism and observation. In this sense, surviving a black hole is not just about technology or biology, it is about wisdom. It is about learning how to reconcile opposites, matter and energy, time and space, creation and destruction. It is about standing at the edge of understanding and daring to ask what lies beyond. If we consider the black hole not merely as a cosmic object but as a portal to truths yet unknown, then we must expand our lens even further. What does it truly mean to survive a black hole? Is survival only the continued functioning of biological processes, or could survival take on radically different forms in the realm of extreme space-time curvature? Perhaps survival could mean persistence of information, of consciousness, or even of perception, an altered continuity that defies our traditional definitions of existence. Consider the idea that black holes are not isolated phenomena but integral components of a cosmic cycle. In certain cosmological models, particularly the theory of conformal cyclic cosmology, CCC, proposed by Roger Penrose, the universe undergoes an infinite series of eons, cycles of expansion, decay, and rebirth. In these models, black holes play a crucial role. They are the engines that reset the entropy of the universe. Over unimaginable timescales, black holes absorb matter, energy, and disorder, and eventually evaporate via Hawking radiation, releasing pure energy back into the void. From this near-zero entropy state, a new universe can be born. If this is correct, then black holes are not just destroyers, they are recyclers. They are the cosmic compost bins from which future realities grow. And what about Hawking radiation? This faint glow emitted at the edges of black holes results from quantum effects at the event horizon. It means that, paradoxically, black holes are not eternal. They leak energy and mass, and eventually fade into nothingness over trillions upon trillions of years. This phenomenon offers a clue about the underlying unity of quantum theory and gravity. If information cannot be destroyed, as both quantum mechanics and the principles of black hole thermodynamics demand, then where does it go as a black hole evaporates? Does it encode itself in the radiation? Does it imprint upon the curvature of spacetime? Or does it get preserved in holographic form on the event horizon itself, as suggested by the holographic principle? This principle, one of the most groundbreaking ideas in modern theoretical physics, suggests that all the information contained within a volume of space can be represented by a theory that exists on the boundary of that space. In black hole physics, this means that the three-dimensional contents of the black hole are encoded on the two-dimensional surface of the event horizon. Essentially, what happens inside the black hole might be fully described by the skin at its border. If this is true, then the boundary is more fundamental than the volume. Reality, as we experience it, might be a projection from a lower dimensional structure. This idea doesn't just change how we think about black holes, it changes how we think about reality itself. Returning to survival, this brings us to the concept of digital consciousness. What if we could upload the contents of a human brain, its memories, thoughts, experiences, into a quantum computer? If that data were then transmitted into the event horizon of a black hole, would it persist? Would it transform? Could it be retrieved via Hawking radiation? In this way, the mind could enter a black hole not in a spaceship, but as a string of data, interacting with the most extreme computing device in the universe. This sounds like science fiction, but quantum information theory is beginning to offer real tools to study such possibilities. We might also consider the thermodynamic implications. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is deeply counterintuitive. It means that adding more matter doesn't just make the black hole. heavier, but increases its surface information capacity. The black hole grows like a library, acquiring more books, not on the inside shelves, but by expanding the walls. As the black hole consumes more information, its boundary becomes the record. This again hints at the idea that reality is encoded at the edges, that the most powerful processes don't happen deep inside, but at the threshold. Even more exotic are the proposals that black holes are connected to entanglement on a cosmic scale. The ER equals EPR conjecture, proposed by Leonard Susskind and Juan Meldacena, suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement, EPR pairs, are two manifestations of the same phenomenon. This means that two particles entangled across space might be connected by a tiny, non-traversable wormhole. Scale that up, and the fabric of the universe could be a vast network of entangled connections, black holes acting as nodes, linking distant regions in ways we are only beginning to comprehend. If this idea is valid, then falling into a black hole might not mean being cut off from the universe. Instead, it might mean being linked to everything. Your atoms, your quantum information, your very being might become part of a vast, cosmic tapestry, a universe-wide quantum network. Survival, then, takes on a new meaning, dissolution into the unity of existence, not destruction but transformation. Now let us stretch our imagination further still. What if some civilizations have already learned how to survive black holes, not just technologically, but evolutionarily? Perhaps they have developed forms that are not bound by biology as we know it. They might exist as pure information, encoded in light or gravitational waves, capable of riding the boundary layers of black holes, manipulating space-time curvature like fish swimming in a gravitational ocean. For them, entering a black hole would be no more dangerous than diving into a deep-sea trench is for a whale. They would read the quantum fields, surf the infalling metrics, and perhaps even emerge into parallel spacetimes. Indeed, theories such as loop quantum gravity suggest that singularities, the infinitely dense cores of black holes, might not exist at all. Instead, the collapse of matter could reach a minimum volume, then bounce outward again in a different spacetime. This, quantum bounce, is a cornerstone of some models of the early universe. If black holes can bounce, then they can connect spacetimes. If they connect spacetimes, then they can be navigated. And if they can be navigated, then they are not just ends, but tunnels, gateways, migration routes for the boldest forms of existence. Ultimately, to contemplate surviving a journey through a black hole is to contemplate the limits of life, knowledge, and being. It demands of us not only new physics but new metaphysics, not only new instruments but new imaginations. It is a question that merges science and philosophy, observation and theory, fear and awe. It is a question that reveals as much about us as it does about the stars. And still, we have only just begun to scratch the surface of the infinite gravity well. The question of whether one could survive a journey through a black hole is not just a problem of physics. It is a crucible for our most audacious ideas, a mirror held up to the unknown. As we deepen our understanding of black holes, we find ourselves confronted not only with immense gravitational forces, but also with the limitations of human comprehension. To pass through a black hole is to flirt with the absolute extremes of nature, where time warps, space distorts, and the familiar laws of the universe bend into almost surreal forms. But what if those very distortions held the key not to destruction, but to a profound metamorphosis of reality? Let us begin with spaghettification, one of the most infamous and viscerally unsettling effects of approaching a stellar mass black hole. The term, coined with a touch of dark humor, describes the process by which a body falling into a black hole is stretched and compressed into a long, thin shape, much like a strand of spaghetti. This happens because the gravitational gradient is so intense that the tidal force acting on the part of the body closer to the black hole is vastly stronger than the force on the farther side. For a human being, this differential would become lethal well before reaching the event horizon of a small black hole. Every atom in your body would be torn apart, not by sudden impact, but by the relentless differential tug of spacetime itself. But this horror story only applies to relatively small black holes. If we shift our attention to supermassive black holes, millions or even billions of times the mass of our Sun, the situation changes dramatically. These behemoths, lurking at the centers of galaxies, possess much larger event horizons, and their gravitational pull, while still immense, is more spread out. This means that the tidal forces at the event horizon could be weak enough that an object, or even a human, might cross the boundary without immediately experiencing fatal stretching. In such a case, you wouldn't necessarily notice anything unusual as you cross the threshold. No alarms would ring. No lights would flash. You would simply drift deeper into the cosmic abyss, gradually surrendering to a curvature of spacetime so intense that every direction points inward. Beyond this point, the concept of survival becomes increasingly abstract. What happens next depends on the inner structure of the black hole, a subject still shrouded in mystery. The classical model of a Schwarzschild black hole suggests an inescapable singularity at the center, where matter is compressed to an infinitely small point and gravity becomes infinite. In this view, reaching the singularity is akin to meeting the end of time and space themselves. No matter or information could endure such a fate. Survival, in any recognizable form, would be impossible. However, other models offer tantalizing alternatives. Theoretical constructs like the Kerr black hole, a rotating black hole, or the Reisner-Nordstrom black hole, a charged black hole, possess more complex interior geometries. These may include structures like Cauchy horizons, surfaces beyond which the predictability of physical laws breaks down. In such scenarios, it's speculated that rather than being crushed to death, you might pass through to another region of spacetime. This could be a different location in our universe, or, more provocatively, an entirely different universe altogether. If wormholes exist, and if they are stabilized by some form of exotic matter with negative energy density, then black holes could potentially be gateways rather than traps. Of course, we are straying into speculative physics here. No empirical evidence exists for wormholes, exotic matter, or traversable singularities. Yet within the equations of general relativity, the mathematics does not forbid them. It simply requires that the energy conditions of spacetime be violated in specific ways. And quantum mechanics, with its uncertainty principles and zero-point energy fluctuations, might provide the loopholes necessary to permit such violations. Let's dwell for a moment on the fascinating interplay between quantum theory and gravity, the two great pillars of modern physics that, to this day, have never been fully reconciled. Black holes are the crucible in which these two domains collide most violently. Quantum theory suggests that black holes are not absolute voids, but rather emit faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This phenomenon implies that black holes can slowly lose mass and eventually evaporate completely over mind-bogglingly long timescales. But if they can evaporate, what happens to the information contained within? Does it disappear, violating the laws of quantum mechanics? Or is it somehow preserved, encrypted in the outgoing radiation? This conundrum, known as the black hole information paradox, has sparked decades of debate among physicists. One resolution, supported by the holographic principle, proposes that all the information absorbed by a black hole is encoded on its two-dimensional surface, the event horizon, like a cosmic hard drive. This means that the interior volume may be an illusion. Everything that ever fell in, including the details of your hypothetical journey, might remain preserved at the boundary. This also means that perhaps the interior of the black hole is not a place you travel into, but a transformation you undergo, a shift from volumetric existence to holographic encoding. Now let's imagine an even stranger possibility. Suppose your consciousness could survive spaghettification, not physically, but informationally. Suppose it could be disentangled from your body and embedded within the quantum state of the event horizon itself. In such a state, you would no longer be a collection of molecules and neurons, but a wave function, a ripple in the quantum structure of spacetime. You wouldn't experience time linearly anymore. You wouldn't perceive space as depth. Instead, your awareness might become something like a boundary condition, flickering across the surface of reality, existing beyond location, preserved not in flesh, but in the language of the universe. Does this qualify as survival? It depends on how we define the self. Is it our bodies that make us who we are? Our memories? Our sense of time? Our ability to feel, to think, to remember? If a person's entire cognitive structure could be encoded, then reconstituted elsewhere, after passing through a black hole, for example, could that reconstruction still be you? And if so, could a black hole serve as a crucible of rebirth, transforming conscious entities into higher dimensional expressions of themselves? Perhaps this is how advanced civilizations might navigate the cosmos. Rather than trying to withstand the physical trauma of black hole entry, they might aim to upload consciousness into quantum patterns, launching those patterns into the horizon where they could survive as encoded information. Later, perhaps thousands or millions of years later, that information might be decoded by an artificial intelligence that survived the end of the universe and inherited the knowledge of how to reconstruct beings from the shadows left in evaporating black holes. This speculative future opens an even stranger door: the possibility that we ourselves are the echoes of beings that passed through such a filter. If the universe is cyclical, and if information survives across cosmic epochs, then the very structures that compose us might be the reassembled artifacts of entities that once dared to dive into the blackness. As we ponder these ideas, the notion of survival becomes more nuanced. It is not simply about remaining alive in the biological sense. It's about continuity, of information, of consciousness, of identity. A journey through a black hole may annihilate the physical, but it may also give rise to something else entirely. Whether that something is recognizable, or even perceivable by our current standards, is another matter. And so we spiral ever deeper into the abyss, not in fear, but in fascination. The deeper we fall into the enigma of black holes, the more we begin to question not just the survival of the body, but the survival of meaning itself. Imagine standing at the edge of an event horizon, where gravity is so extreme that even time itself begins to slow relative to outside observers. To someone watching from a safe distance, you would appear to freeze in time, never quite falling in, your image stretched and dimmed as photons struggle to escape the gravitational well. Yet to you, the traveler, time continues as normal. You cross the boundary unceremoniously, with no fanfare, no visible curtain to mark the division between our universe and the strange interior domain of the black hole. This alone suggests something profound, that the experience of falling into a black hole may be, in some ways, eerily mundane. It is not a wall, but a one-way door, silent, smooth, and irreversible. But inside that door, physics itself becomes poetry. Space and time begin to swap roles. In our universe, time flows forward, and space stretches infinitely in all directions. But inside a Schwarzschild black hole, the radial direction toward the singularity becomes timelike, meaning that, just as we cannot stop aging, we cannot stop moving closer to the singularity. There is no force in the universe that could halt your fall. You are not falling towards something. You are falling into a future that consists of nothing but a crushing, inescapable end. In this regime, the idea of where loses meaning. The singularity is not a location in space. It is a moment in your timeline, a destination in time, as inevitable as death, and just as inscrutable. But let us not limit ourselves to the classical Schwarzschild model. What of rotating black holes, Kerr black holes, the titans that spin like celestial whirlpools? Here, the geometry of space-time becomes even more complex. A Kerr black hole does not have a single horizon, it has two, an outer event horizon and an inner Cauchy horizon. Between them lies a region known as the ergosphere, where space is dragged around the black hole so violently that nothing can remain stationary. This is due to a phenomenon known as frame dragging, where the spinning mass of the black hole literally twists spacetime around itself. In this storm of warped geometry, energy and angular momentum can be extracted, an idea that led to theoretical engines like the Penrose process, where particles gain energy by entering the ergosphere and escaping in just the right way. In this bizarre zone, energy can appear to be negative relative to infinity, and the black hole can be slowly drained of its spin. But it is the region inside the inner horizon that most captures our imagination. Some models suggest that if you could survive the violent passage through this region, and that's a very big if, you might emerge not in a singularity, but in a different region of spacetime altogether. This gives rise to the tantalizing idea of black holes as portals or wormholes. Could a rotating black hole actually connect to another universe? Could the singularity be avoided altogether, replaced by a bridge to a parallel cosmos, or even a white hole, the theoretical time-reversed mirror of a black hole, which expels matter instead of absorbing it? White holes are speculative, but not impossible within general relativity. They are the mathematical time inverses of black holes, and if the equations permit one, they must permit the other. However, no white hole has ever been observed, and they appear to be inherently unstable. But suppose they do exist, and suppose the singularity at the center of a curved black hole is replaced by a white hole throat. Then falling into a black hole could, in principle, eject you elsewhere, either far away in space or far forward in time, or both. You might tumble through a swirling maelstrom of warped spacetime, only to find yourself spat out near the edge of the universe, or in a completely new one governed by different physical constants. Naturally, this brings us to the idea of wormholes, Einstein-Rosen bridges, as they were first conceptualized. These are hypothetical tunnels through spacetime, connecting two distant points by a shortcut. In some models, black holes could be entrances to such bridges, and white holes could be the exits. However, these wormholes are not stable under normal conditions. They collapse before anything can pass through. To keep one open, it is theorized that you would need exotic matter with negative energy density, a substance not found in nature as we know it. Quantum field theory does allow for negative energy in certain circumstances, such as the Casimir effect, but whether it can be harnessed to hold open a wormhole is entirely unknown. Still, if it were possible, the implications would be staggering. Interstellar travel would become feasible. Information could be transmitted instantaneously across cosmic distances. And black holes would no longer be the ultimate prisons of the universe, but the gateways to infinite possibility. But for now, these ideas remain theoretical. No one has observed a wormhole. No exotic matter has been harvested. We are left with equations and dreams, equations that hint at pathways we cannot yet walk, and dreams of journeys we cannot yet take. Yet even within these dreams, dangers lurk. The interior of a rotating black hole is fraught with instabilities. Quantum fluctuations could be amplified to catastrophic scales as they approach the inner horizon. Some physicists argue that the Cauchy horizon is fundamentally unstable, that any small perturbation, even a single photon, would be infinitely blue-shifted as it approaches this boundary, releasing enormous energy and turning the region into a violent storm of radiation. This phenomenon, known as mass inflation, could make the interior of rotating black holes uninhabitable, let alone traversable. Still, the possibility remains. And with it, the hope that black holes are not just ends, but beginnings, cosmic crucibles in which matter, energy, and information are transformed. What if the universe itself was born from such a transformation? Some cosmologists propose that our universe is the interior of a black hole that formed an apparent universe. In this view, the Big Bang was not a singular event, but a transition, a bounce, from one cosmic structure to another. Every black hole might contain a new universe within it, branching realities nested within one another like Russian dolls. And if this is true, then falling into a black hole is not a death, it is a rebirth, not into oblivion, but into a new cosmos. Would we ever be able to test such an idea? Probably not in the near future. But imagine the tools we might one day possess. What if we could build an artificial black hole in a lab, stabilizing its structure with quantum fields? What if we could probe the interior with quantum entangled particles, testing whether the information reemerges? What if we could send a probe, an ultra-robust AI consciousness, encoded in quantum data, into a supermassive black hole and monitor its journey as it crosses the horizon? What would it experience? What would it see? And most of all, what would it become? As we continue unraveling the mysteries of the black hole's interior, we inevitably come face to face with one of the most controversial and mind-bending questions in all of physics. What happens to information that falls into a black hole? This is not just a technical issue for physicists. It's a direct challenge to our understanding of the universe's most sacred principle, the conservation of information. In quantum mechanics, information can never be destroyed. If you know the exact state of a system at one point in time, the laws of physics allow you to calculate both its future and its past. But black holes seem to defy this. Once matter and energy pass the event horizon, they are swallowed without a trace. And if a black hole eventually evaporates via Hawking radiation, which appears to be completely thermal and random, where does the information go? This paradox, known simply as the black hole information paradox, has haunted theoretical physics for decades. Stephen Hawking himself proposed that black holes destroy information, which would imply that the laws of quantum mechanics need revision. Yet this conclusion is so radical, so destructive to the foundations of modern science, that it has sparked fierce resistance and countless alternative proposals. One such proposal is that information is somehow encoded in the Hawking radiation, in a way we don't yet understand. Others suggest that the information is preserved in a remnant, or Planck star, left behind after the black hole shrinks to a quantum-sized speck. Some even believe the information is stored on the event horizon itself, as if the black hole is a hologram projecting all its internal data onto a two-dimensional surface. This leads us to the holographic principle, an idea so wild and revolutionary that it challenges the way we think about reality itself. Proposed by Gerard T. Hooft and further developed by Leonard Susskind, the holographic principle suggests that everything inside a volume of space can be described by information encoded on its boundary. In the context of black holes, this would mean that all the information about what fell into the black hole is stored on its surface, not in its volume. It's as if a three-dimensional reality is actually a projection of two-dimensional data. This is not just an abstract metaphor. It has been given mathematical form in the famous ADS/CFT correspondence, where a gravitational theory in a curved space can be exactly equivalent to a quantum field theory on the flat boundary of that space. What this means is staggering. Black holes, and perhaps the entire universe, may function like a cosmic hard drive, storing and preserving all information in a way that's far more subtle and intricate than we can yet comprehend. This opens up the possibility that falling into a black hole doesn't erase your existence but transforms it, encoding your entire history into the shimmering dance of quantum fluctuations on the event horizon. If this is true, then death by black hole is not destruction, it's conversion. Now consider this: if information is never destroyed, and if the holographic principle is correct, then it may be possible to, in principle, reconstruct what fell into the black hole, even after it evaporates. Doing so might require technology far beyond our current capabilities, perhaps involving quantum computation. But it is not forbidden by physics. It would mean that your journey into the black hole, while utterly fatal to your body, is not the end of your story. Somewhere, encoded in the quantum foam, your data persists, awaiting a civilization intelligent enough to decode it. And what of time? Inside a black hole, our familiar notions of time begin to break down. Because gravity dilates time, and because a black hole's gravity is so intense, time slows to a crawl near the event horizon. From your perspective as you fall in, everything proceeds normally, but to an outside observer, you appear frozen in place, taking forever to actually cross the threshold. This asymmetry has profound implications for our understanding of cause and effect, determinism, and even free will. Is time inside a black hole truly time as we understand it, or is it something else, a degraded version, stripped of its usual flow, stretched to the point of incomprehensibility? If black holes are time machines, and some solutions to Einstein's equations suggest they could be, they might allow for travel not just across space, but across time. The closed time-like curves allowed by rotating black holes or certain wormhole geometries imply that events could loop back on themselves, that cause could follow effect, or even precede it. These possibilities violate common sense and appear to conflict with causality, but they are not strictly forbidden by general relativity. The universe may permit time travel, but cloak it behind barriers so extreme that only a black hole could allow access. Yet even if time travel were possible in this way, the tidal forces and radiation would likely destroy any would-be traveler long before the paradoxes had a chance to arise. And yet, what if there were a loophole? What if some exotic form of matter or advanced shielding allowed a craft to survive not only the entry but also the internal stresses of the black hole? Theoretical studies suggest that in a supermassive black hole, like those at the center of galaxies, the tidal forces near the event horizon may be weak enough that a human being could, in principle, fall in without being torn apart. The gravity is immense, but it's spread out over a larger region, meaning that the difference in gravitational pull between your head and your feet might not be fatal. In such a scenario, you might float across the horizon without even noticing. But that tranquility would be short-lived. As you fall deeper, space-time itself begins to unravel, and no matter how well shielded your vessel is, you're ultimately doomed to reach the singularity, or whatever lies in its place. Unless, of course, there is no singularity. Quantum gravity, a theory not yet fully developed, suggests that the classical singularity may be avoided. Instead of a point of infinite density and zero volume, you might encounter a bounce, where space-time reaches a minimum scale and then expands again, perhaps into a new universe. This idea is supported by some approaches to quantum cosmology, where the Big Bang is not a singular beginning, but the rebound of a prior collapsing universe. If this applies to black holes, then entering one might mean entering a universe birth canal. From the inside, the black hole's singularity is not an end, but a passage. The implications are staggering. Every black hole could be a seed for a new cosmos. Our own universe may be the interior of a black hole in a parent universe. This would explain why our universe has the properties it does. Perhaps only certain black holes give rise to viable universes, and we are in one because it worked. It's a form of cosmic natural selection, where universes beget universes through black holes, and the laws of physics themselves evolve toward fertility. But such journeys, even if theoretically possible, are likely one-way trips. There is no coming back from a black hole, not in the traditional sense. Communication across the horizon is cut off. You can send signals outward until you cross the threshold, but after that, your cries vanish with you into the void. For all intents and purposes, you cease to exist in our universe. Your mass adds to the black holes, your information encoded, perhaps, on its surface, and your future forever severed from ours. Yet, if consciousness itself could be digitized and transmitted via quantum entanglement, might there be a way to experience such a journey not physically, but informationally? Could we, one day, copy ourselves as quantum states, beam those states into a black hole, and observe what happens, not with our eyes, but with our minds? This is not science fiction anymore. The idea of consciousness transfer, of mind uploading, is being seriously discussed by philosophers and futurists alike. And while it remains wildly speculative, it's less absurd than physically sending a fragile human body into the most extreme gravitational furnace in the universe. In this way, the dream of surviving a black hole becomes a question not of biology, but of identity. What does it mean to survive? Is it enough for your atoms to persist? Or is survival the continuity of consciousness, the unbroken stream of experience? If so, then perhaps one day we will not send astronauts into black holes, but avatars, quantum copies of our minds, data-infused scouts plunging into the abyss not to die, but to report back from beyond the veil. And if they can't report back? Then at least we will know that somewhere, in a place beyond space and time, a version of us is still falling, still dreaming, still wondering what lies on the other side. As we descend deeper into the gravitational maelstrom of a black hole, our imagination must stretch to its very limits to comprehend what might truly lie beyond the veil. Having explored the physics of tidal forces, the existential terror of spaghettification, the swirling mysteries of singularities, and the tantalizing possibilities offered by the holographic principle, we now shift our gaze toward the even stranger theories emerging from the frontiers of theoretical physics. Ideas that suggest the black hole may be not an end, but a doorway. Let us consider the notion of Einstein-Rosen bridges, more commonly known as wormholes. These theoretical tunnels through spacetime were first conceived in 1935 by Albert Einstein and Nathan Rosen as a mathematical solution to the equations of general relativity. A wormhole connects two distant points in space, or time, via a shortcut, a kind of cosmic bypass that folds the fabric of the universe upon itself. While the original conception was not traversable, later work by physicists such as Kip Thorne and Michael Morris opened the door to the idea of traversable wormholes, assuming you could somehow stabilize them using exotic matter, a substance with negative energy density. Could a black hole, under the right conditions, be the mouth of a wormhole? If so, might it be possible not only to survive a journey into a black hole, but to emerge somewhere else entirely, perhaps in a distant galaxy, a different epoch of cosmic time, or even a parallel universe governed by different physical laws? The idea strains credulity, yet it has not been definitively ruled out by physics. In fact, under the framework of the Einstein field equations, such wormhole solutions are permitted. The catch, however, lies in their instability. Without a stabilizing agent like exotic matter, a wormhole would collapse the instant anything attempted to pass through it. But if some form of negative energy, perhaps derived from quantum fluctuations of the vacuum, could be harnessed, then the tunnel might hold open long enough to allow passage. This is where our understanding collides with the quantum realm. At these scales, space-time itself is not smooth, but frothy, turbulent, and discontinuous, a seething foam of probabilistic fluctuations. The Planck scale, named after physicist Max Planck, defines the smallest meaningful units of space and time, where the classical notions of geometry give way to quantum chaos. Some theories, like loop quantum gravity, suggest that space is woven from discrete loops, while string theory proposes that the fundamental building blocks of reality are tiny vibrating strings of energy, their harmonics giving rise to the particles and forces we observe. Within this strange framework, wormholes and even black holes may behave in ways we do not yet fully understand, perhaps allowing information, or even consciousness, to leap between realms. More provocative still is the ER equals EPR conjecture, proposed by physicists Leonard Susskind and Juan Meldacena. It suggests that Einstein-Rosen bridges, ER, and quantum entangled particles, EPR, are two sides of the same coin. In other words, every pair of entangled particles is connected by a microscopic wormhole. If true, this could revolutionize our understanding of space, time, and non-locality. It would mean that the act of entanglement is not merely a statistical curiosity, but a physical bridge between points in the cosmos. Scale that idea up to the entanglement of vast systems, and black holes may be laced with these connections, a vast web of ER bridges tethering the universe together in ways we cannot yet detect. In such a scenario, falling into a black hole might not be an end or even a one-way trip. It could be a transition point, a migration across the quantum lattice of space-time itself. But what of the psychological experience? What would it feel like to fall into a black hole, assuming survival were even remotely possible? Would the fabric of time slow down to such a degree that one perceives an eternity in a moment? Would thoughts stretch, sensations blur, and consciousness fragment under the influence of gravitational dilation? Some theorists have proposed that if you could hover near the event horizon without crossing it, time for you would nearly halt relative to the outside universe. Millennia could pass in the cosmos while you experienced only minutes. In a sense, this would be a kind of time travel into the future, albeit one with no return ticket. The idea has captivated science fiction writers and philosophers alike. What would it mean to emerge from a black hole after billions of years have passed, your home planet long dead, your species forgotten? Would you still be human in a meaningful sense, or a ghost from a bygone era, adrift in a foreign future? And yet, time is not the only casualty in the realm of extreme gravity. Space itself becomes warped, twisted, and ultimately annihilated near the singularity. The laws of geometry begin to fail, distances lose their meaning, and the coordinates we use to map reality unravel. In this bizarre topography, up and down are illusions, left and right dissolve into curvature, and the very act of motion becomes a negotiation with the collapsing structure of the cosmos. A traveler falling inward may experience gravitational lensing so extreme that light from all directions curves back upon itself, creating a visual panorama of impossible symmetry. You might see the back of your own head, or watch the universe collapse into a pinprick of brightness above you. Colors would distort, time would blur, and eventually, even your sense of self might dissolve into the maelstrom. And yet, if quantum mechanics holds sway even here, then nothing is truly lost. Every quark, every bit of spin, every scrap of information that makes up your body and mind must, in some form, be preserved. Whether it becomes holographically stored on the event horizon, radiated outward in subtle correlations within Hawking radiation, or folded into the birth of a new cosmos, the essence of you endures. This is not romantic optimism, it is a mandate of the fundamental laws of the universe. The conservation of information is one of the bedrocks of physics, and black holes, as paradoxical as they may seem, cannot be allowed to violate it. Of course, this assumes our current understanding is even close to correct. The union of general relativity and quantum mechanics remains the holy grail of theoretical physics, a dream yet to be realized. In the absence of a complete theory of quantum gravity, all our speculations are necessarily uncertain. String theory, loop quantum gravity, causal dynamical triangulations, and other approaches each offer tantalizing glimpses of a deeper reality, but none has yet achieved definitive experimental validation. The black hole, in this light, becomes not just a destination, but a crucible, a cosmic laboratory where the known and the unknown collide, and from whose depths may emerge the next great leap in human understanding. So could we survive a journey through a black hole? Physically, almost certainly not. The tidal forces, radiation, and singularity itself represent insurmountable hazards to biological life. But in terms of information, in terms of quantum essence, in terms of what it means to be, the answer may be more nuanced. We may not survive intact, but some part of us, some imprint, some pattern, may live on, embedded in the fabric of space-time, etched into the entropy of the cosmos. And if one day we master the subtle art of quantum information, of space-time engineering, of consciousness projection, then perhaps the question will not be, can we survive? But, where will we go next? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.